Raz, dva, raz, dva.
Okay.
Raz, dva.
Good morning, ladies and gentlemen. It's my great pleasure and honor to welcome you at the premises of the Czech Institute of Informatics, Robotics and Cybernetics, abbreviation CIIRC, of the Czech Technical University. This is the youngest research institute of the Czech Technical University, established in 2013, 9 years ago. In the years 2014 to 2017, we were constructing this building, which was opened in 2017. Currently, the institute has got 210 researchers, plus 100 PhD students, and it's quite strong research body, well equipped. There are many international projects, and I would like to invite you to visit our facility later in the afternoon. There is quite unique test bed for Industry 4.0. It occupies the space 1,700 square meters, and it's equipped with tens of robots, 3D printing machines, 5G communication systems, and so on and so on. You can see it. So this is quite unique, and we continue in the support of this facility by testing and experimental facilities, brand new program of European Union. So please feel here like at home and enjoy the second day of the workshop. Yesterday it was quite interesting and successful event. I hope also today will continue very successful, interesting, scientific and technical discussion. And please enjoy the space here. Thank you very much for coming, visiting us. Thank you.
Thank you, Vladimir, for hosting us. And welcome, everybody. My name is Didier Henrion, and I'm delighted to chairing this morning session on mathematics optimization for AI with my co-chair, Jakub Mareczek, who is just right here. And without further ado, I will introduce with great pleasure the first speaker, with Jérôme Bolt from Toulouse School of Economics. And we'll be speaking about non-smooth automatic differentiation.
Thank you, Didier. And thank you, everyone, Jakub, Joseph, Véronique. It's a very nice invitation, and I'm very impressed by what is done here in Czech Republic. So thank you for this invitation. Okay, so my talk is about automatic differentiation. I would like first to have a quick word on what is it. It seems technical. I would say, perhaps in a provocative manner, that learning in AI is basically tuning weights of neural networks or some other system. And for tuning, you need to differentiate. And so automatic differentiation, autodiff in short, is a super fast algorithm for differentiating. And one of its strengths is that it applies to most numerical programs, from solvers to algorithm and all that. And if I wanted to make a provocative statement, I would say that training a deep learning, training a neural network is basically aggregating automatic differentiation operations. Okay? So this is very important. But there is a serious issue in that thing, which is that modern programs are non-differentiable by nature. And since we want to differentiate, well, we have a problem. So it is easy to see this non-differentiability issue by looking at conditional statements in programs. By conditional statements, I mean the if, then, else. And these type of things create naturally branches. And on branches, you have different functions which have different values, and this creates non-smoothness. Okay? You have other way of creating, I don't know it, yeah, to non-smoothness, but this one is essential. And you see here with the ReLU function, you have a zero function and identity. And it creates a non-smooth point. Okay. To analyze this issue, we are going to focus on a special method, which is called the backpropagation algorithm. So it goes like that. So you have a function, which is a composition of elementary functions, basically addition, multiplication, and basic functions. And the backprop algorithm is a very fast instantiation of the chain rule. Okay, so we apply the chain rule on this, and we compute the chain rule backward. Okay, and it's a way to go very fast with the chain rule. And as I said, the problem we meet is that we have non-smoothness. So we have to deal with this non-smoothness. Okay. So how do we do that? We need to use this Clark Jacobians, and Clark Jacobians are a way to modelize differentiation of non-smooth point. So at a non-smooth point, you define a subgradient as the limit of neighboring points. So you obtain a bunch of subgradients like that, and you are allowed to convexify this guy. Okay? So here, these guys represent non-smooth derivative. And so we have our non-smooth derivative. So let's wrap up with the backpropagation algorithm. We start with function like that, okay, a composition, and we differentiate this. We apply the chain rule, and here we put Clark Jacobians, okay. But the problem, the major problem, is that the chain rule does not hold. We are not allowed to do that. In the sense that the object we obtain is not a Clark Jacobian. So we get out of the class. And the thing which is very surprising is that this approach, which is used everywhere in the world, in all softwares and libraries, is that it works remarkably well. And since it works, we would like to understand why it does. Okay, so we stick to practice and we accept this imperfection and see what we see. Okay, so let's have a look at what problem we can face with this approach. So here I have programmed the function 1/3. It's constant. Its value is 1/3. But its program is a bit weird. It is like that, okay? So the function is here, and the program is here. When you differentiate applying the chain rule, you get a derivative at 0, which is 1, which is not very natural, right? And you can do even worse thing, because if you adapt a bit all that, you can program the identity function in a weird way, and the derivative of the identity at 0 is 0. So this time you create an artificial critical point, which is not wishable because critical points are the place where algorithms are stuck. Okay, so given a locally Lipschitz continuous function, we would like to define an object that model all these things. So it should allow spuriosity, so this weird behavior. It should allow derivation, and it should match backprop. Okay? So it's a bit special because we want to allow a loose behavior, but we want also to be sharp to keep the variational content of the process. Okay? And so to do that, we are going to apply this ID. We take a function, and we say that this bunch of gradient we would like to describe satisfies a weak chain rule along curves. So it is an identity like that, in which you have, let's say, a C1 curve to start, and the differential of your function is like that, like in the chain rule. But, oh, sorry. What happened? Yeah, okay. Here, you can choose any subgradient you want in that place. And it has to be to coincide with that for almost all t. Okay? So this is the central definition we have. And so I would like to comment a bit on this formula, which is quite natural. First, it means that the process sees curve. Because on a curve, and if you know the derivative of this, you can rebuild f. But on the other hand, it is blind to zero measure set on curve. So it allows periodicity. So we have a trade-off between sharpness and looseness. Okay? And it goes the same for general function with conservative Jacobians. And now I would like you to remind this definition. If a function has a conservative field, so if there is a guy that satisfies that, then it is called path differentiable. Okay? So we have, if we have that, we are called path differentiable. Okay, and now let's see what we obtain with this type of definition. So I have just recalled the definition there. So here I am listing the main property. The first one is that path differentiable are ubiquitous. So for those who know, definable functions which are locally Lipschitz are automatically path differentiable. This is due to stratification. And for those who don't know, it basically means if you have a function that you can write with a general formula, with sinus, cosinus, max, whatever, polynomial, then you have a path differentiable function. So basically, almost all functions you see are path differentiable. Now, what is a natural conservative field for a path differentiable? Well, the Clerk subgradient does the job. And it's actually the smallest. Something else about this conservative gradient and their variational content, they coincide almost everywhere with the gradient. So we have very strong variational content. And it's easy to see the chain rule holds in general now, okay, not only on curve. You have the chain rule. Okay, so we have a calculus that comes with this function. Okay? So, as I said at the beginning, backpropagation is central in artificial intelligence. And now we have this tool to understand it. And what will happen is basically that backpropagation is a conservative field, almost. If you take the convex envelope, it's a conservative field. Okay? So we understand now this object, and we are able to obtain guarantee, obtain theorem in artificial intelligence related to this backpropagation. So we start with the object itself. So you have a loss, standard loss, which is in the form of a sum. And the first, so this guy is Lipschitz and definable. So the first thing we have is that the backpropagation is equal to the gradient almost everywhere. This was not known. That's quite incredible, but people used it, but it was not proved anywhere. And you need witness stratification, so it's not so easy. It is the same here. You have this identity. And so this thing is a conservative field. And there is something also with which we have to be careful. You can have a 0 for backprop, which is not critical. These are the artificial critical points I was mentioning at the beginning. Okay? So this is what we can say for backprop. We can go a bit further and see why backprop is fast. Why is it so essential to AI? So for this, we need a bit of notation. So given a neural net, let's say with ReLU activation, we are going to cost arithmetic computation, meaning plus, times, and ReLU. They have all the same cost for in this talk. And I count the minimal number of this computation to evaluate my network. I form the loss of my network, the square loss, and I do the same. I evaluate. I count all the operation I need. Okay? And now the question is, what is the cost of computing the gradient, the backprop on L? It would be tempting to say that it depends on the dimension, because a gradient is many coordinates, the number of the dimension. And with the theory we have this theorem which says that backpropagation achieves this complexity result. Computing L and backprop L is not more costly than 5 times L. So I guess this is the reason why we can train deep neural network. It's super fast. It's super fast, and there are no dimension terms in this thing. There is one in L, of course, but not in backprop. Okay, so backprop is cheap to compute. Now, some word about training. So you all know that very well. So we have an empiric sum. We do stochastic gradient. Okay, we draw uniformly at random some of the guy, and we do a gradient in that direction. And this is how we train the network. And the question is, does it reach critical point, and does it reach local minima? And what about artificial point? Also, artificial critical point. So we have this theorem, which is too long. So long story short, with probability 1, you reach only Clark critical point with this method. And even more, it's not written, but it's doable, so young people should perhaps do that. You can prove that generically you reach local minimizers. Okay? So that's, of course, important for IA. So maybe 2 last results. So here it's about implicit network. So here you have layers that are implicit, which means that they are obtained by solving an equation or an optimization problem. They are known to be a bit more efficient than usual layers. You need less implicit layers than usual layers. So let's take a layer like that. X is the entry, and Y is the output. Okay. So like that. And we would like to propagate derivative in this network to train it. So how can we do that? Well, for engineer, it's very simple. You take the equation, you write this formula, you differentiate. You don't care, of course, of differentiability. And then you invert, and you have your formula. But of course, it's not like that normally, because this object is non-smooth, okay? And so we have been able to justify all that. This object, which is a bit weird, is actually conservative under mild assumption, which are similar to the smooth case. And so we can train implicit network using this formula. Okay, and I will end with something which is quite fashionable this time, which is differentiating algorithms. So how does it work? So you have a family of strongly convex problems here. Theta is a parameter. And so you want to solve for this method, okay? But perhaps after you want to optimize in theta, you want to compute the sensitivity in theta, you want to do things with theta. So you run your algorithm. In theory, at the end, you obtain the solution of your method. And the question is, could we compute at the same time the solution and a derivative? So the solution and a variation. And so there is a simple thing to do, which is you have your algorithm like that, and at the same time it progresses, you can compute the derivative just by applying this formula, okay, which is known as piggyback derivatives for obvious reason, because you follow the ferroutage en français. Yeah, in Czech, I don't know. And so you obtain an object, x prime k, which converge, okay? But in general, we don't know to what kind of object it converge, and it can converge to a multi-valued object. And again, here, we have discovered that the limit of this object is a conservative Jacobian. In other words, we can use all the theory on this derivation of algorithm as well to optimize in terms of theta or to do whatever we want with theta. Okay, so I think I'm done. I don't know if I've been too long.
Many thanks, Jérôme, for this survey of foundational work for AI. We have time for, I would say, 2 short questions from the audience, using the microphone, preferably. Joseph?
One quick one. In practice, there is often difference in what algorithm one uses. If one, for the
can you speak?
in practice, there is often difference what algorithm one uses for the optimization. Is it Adagrad or is it just a stochastic gradient descent? Can you also say something about this, or this is still beyond?
You mean the discrepancy between practice and?
Yeah, I mean, it's like, does it depend, or can one say something about what algorithms to also use for the optimization? I know that these were quite foundational results, what you were showing, but...
you mean other algorithm than SGD?
Yeah, for example.
Yeah, well, it needs to be, it needs to be studied, I guess, so there are plenty of things to understand. So simply, if there is an idea beyond that, was to understand what is backprop mathematically. Then we have this answer, and we need to use it to make further studies.
Another one, maybe? Mihai?
Thank you, Jérôme. If we start with splines, let's say, piecewise polynomial functions, is your algorithm performing very fast? Is detecting the partial derivatives and so on?
So in the experiment we have made, we have observed something quite funny. If you have at high precision, you never see the problem. But if you are at low precision, saying 16 bits, you start to see the problem. And at 8 bits, you see almost always the problem. So mathematically, the answer, yes, you can do. And if you
I'm asking because they are finitely determined. You know, a spline is determined by finitely many parameters, and in fact, you should be able to extract from this finite determinateness everything very quickly.
Yeah. But yeah, I would say it works.
It should work.
Yeah, it would work. I think it's past differentiable, and so you can just plug it in here and then boof. Yeah.
It was nice to see Edward at work.
Yeah.
Many thanks. For the sake of time, we have to move forward to the second speaker. Thanks again, Jérôme. And the second speaker of this morning session is Alessandro Rudi, who is from Inria Paris, and who will be speaking about representing non-negative functions.
Well, I would like to thank the organizers for the invitation to this amazing workshop. And today I'm going to speak about, a model for non-negative functions that promises to bring the same benefit that linear models brought to interesting fields like interpolation, approximation, more generally machine learning, but to other fields that are crucial for nowadays applications like optimization, optimal transport, optimal control, reinforcement learning. So this is a work we developed starting in the COVID period when we had nothing to do with my PhD students Ulysse Marteau-Ferré, Boris Muzelek, Francis Bach, and then we extended to other members of the team and other friends. And so, while linear models have been the workhorse in many fields of applied mathematics, like, as we said, interpolation, approximation theory, machine learning, but also quadrature integration problems and solution of PDEs, in particular the meshless methods. Well, if we look at the linear model, we just, so here, what is a linear model? When I say linear model, I mean a model for functions that is linear in the parameters. So here the parameters are theta. And the model is a linear combination of nonlinear functions. So here you can put the basis you like, a subset of, for example, Fourier, wavelet, or a non-parametric basis like G could be a Gaussian centered in some points from your data set. Well, the two properties that made linear models so effective for numerical algorithms are the linearity in the parameters that preserves convexity. So if you plug a linear model in a convex functional, you obtain a convex problem. And then the fact that you can compute linear operators of your function in closed form if your functions G are simple enough. For example, you can compute the integral in closed form for nice nonlinearities. This is the first property. This brings flexibility. The second property is concise approximation. So how many units, this you can see it as nowadays as a neural network with 2 layers. How many units do you need to put to approximate a function of interest? Well, concise approximation is a result that tells you that for a wide choice of nonlinearities, you need a small amount of units to approximate a wide class of functions. So this is a classical result from approximation theory. If you take a function that is m times differentiable and you want to approximate it up to error epsilon, you need the number of units that is in the order of epsilon minus d over m. Why this is interesting? Because if the function is smooth enough, so it is regular, then you need the number of units that breaks the curse of dimensionality. For example, if you take m in the order of d or larger, then you need n in the order of epsilon minus 1 to achieve error epsilon. And so you can really compute it concretely in interesting problems. So those are the two properties. The fact is that not any problem can be solved with a linear model. Some problems need more structure. And here I do some list: probability representation and inference, optimization, optimal transport, optimal control, reinforcement learning. If you see probability representation, you see already that you cannot use a linear model because you need an additional condition. Your function must be non-negative everywhere and also must integrate to 1. Linear model don't work because they cannot guarantee non-negativity. There could be regions where the function goes below 0, and you cannot control it. Okay, so in literature, there are two models for this. More generally, ridge models. So you take a linear function and you map it on the positive semi-axis. For example, you take the exponential of a linear function, or you just restrict the range of the parameters. But unfortunately, both of them lose something. So if you do a ridge model, like an exponential model, you still keep concise approximation, but you lose the linearity in the parameters, so you cannot do the integral anymore. For example, you need to resort to more complex algorithms that have exponential convergence, so they are exponentially slow, like Monte Carlo. If you instead restrict the parameters, you lose. Okay, I'm not able to use this. So you lose so you are linear in the parameters, but you lose. I don't use it anymore. So you lose concise approximation. What does it mean? So imagine that now you are. So why we lose concise approximation? Well, because the model is too rigid. So if you see it's a linear combination. It's a linear combination. Let's take G to be Gaussians for simplicity. Some Gaussians centered on a list of points. Since it is, you are just summing Gaussians, if you want to approximate the green curve, you need to take Gaussians with the width that is smaller. Oh, basta. Okay, I will not use it. With the width that is like the blue curve there, that is smaller than the smallest peak. And this means that if you want to then fill with those Gaussians the big peak, you need to fill the volume of it that is exponential in the dimension. Vice versa, I mean, this is the intuitive reason, and you can show in general that you cannot beat the rate epsilon minus d over 2. So you can never be, even if your function is smooth, better than this rate that is exponential in d. And yeah, so there is no way to be adaptive to the smoothness unless you know exactly which variance to choose at each point, but this is equivalent to learn a non-negative function, so it's the same problem. And this is interesting because if you drop the requirement of non-linearity, of non-negativity, you see that the best linear model to fit this green curve takes a Gaussian that is the red one, that is larger. And how can this approximate the green curve? Via cancellations. So cancellations are crucial to achieve the optimal learning rate. So if you want a model that is linear in the parameters and with concise approximation and also non-negative everywhere, we still to allow a restricted form of cancellation. And so this is why we thought about this general model that many of you already know. And so we are going to talk about the relation between this model and SOS polynomials, because it is clearly an SOS construction. So this model is a generalization of a linear model, is a linear combination so you take a matrix A that is positive semi-definite, and you multiply the element I Aij with the nonlinearity x in xi and the nonlinearity in xj. You see by construction, so if you stack all the functions in a vector, that, so if you call this vector phi, f of a is just phi transpose a phi. So since a is non-negative, for any x, this function will be non-negative, so you have guaranteed non-negativity everywhere. But it is also linear in the matrix A. So you can use, where you can use linear models. It preserves convexity. So if you plug this model in a convex functional, now you can optimize over non-negative functions, obtaining an SDP problem, and you can still compute all the linear operations like integrals. So, for example, you can use it to represent probabilities, being able to compute the integral in closed form. The question is, do we have concise approximation? So, can this model approximate a non-negative function of interest with few units? Okay, so I'm not going to derive it here, but it's easy to show that if your function does, this maybe you can discuss with me, I'll put in R later if you want. So this is easy to discuss, to see that if your function does not touch 0, then of course, in this model, you can represent the square root of an m-differentiable function that does not touch 0, and is so strictly positive, is still m-differentiable. So you can easily approximate this function with this, we call this PSD model, with the PSD model that is of rank 1, and so it is small a transpose with the column itself that is the approximation via a linear model of the square root. And so we have a concise approximation. More generally, we can approximate with faster rates, so rates the same rate of linear models, functions that can touch 0 if the zeros are on a C1 manifold. So this is interesting because we have an easy geometric condition for which we can say if this model can approximate the functions or not. And I mean, it's a quite general condition also. So, what do we do with this model? I said that it could help, could improve some algorithms in interesting fields of applied mathematics. Let's do it for optimization. And so this is the motivation for all the story I told you. So we started from here. From the, I was reading the book of Novak that was showing the equivalence between the optimization and the approximation problem. This is considered in the community of optimization mostly as a curiosity if you take the optimization community as a whole. But this is interesting because on one side, in the side of approximation, we have very refined algorithms that achieve a rate as the one we have seen. But on the optimization side, we don't have the same clarity. So we have either algorithms that solve non-convex optimization, but there are of practical interest, so they don't have rates to achieve the global optimum, or algorithms that achieve the rate, but with guarantees that are not the same guarantees that you have for that you have from approximation theory. But this result, that is non-constructive in nature, tells you that they should be the same rate. So can we achieve an optimization algorithm with the same optimal rates of approximation? And so that beats the curse of dimensionality, at least in the rate. And this is what we are going to see now. And so we just start rewriting the problem of optimization. We want to do non-convex optimization of an m-differentiable function unconstrained, okay? So we assume that there is a minimum in this in the set of definition. So first we do simply so we rewrite the problem in terms of a convex problem. What we are doing here is that we push all the complexity of the problem into this dense set of constraints. So finding the minimum of h is equivalent to find the highest hyperplane below h. now this is an optimization of the parameter C. All the complexity is in this dense set of constraints. As a machine learner, when I see something dense, the first thing I want to do is to discretize it. And if you discretize, you obtain this algorithm. It is just a fancy way to write that you take just the minimum of the function on the list of points you have observed. This algorithm converges to the global optimum eventually, but it is too slow. So, and all the complexities, so it's by elementary arguments, you can show that you cannot beat a rate that is epsilon minus d over 2. So it will achieve, but it is too slow. You cannot beat this rate. Can we do better? Well, we said that we want to use approximation theory, so let's go in this direction. We introduce the function f. So we transform the dense set of inequalities into a dense set of equalities. We introduce the function f that is non-negative and that is equal to h minus c. We know something more because this function is equal to h minus c. H is m times differentiable, so we know that f itself is m times differentiable. And so this is a setting where we have a problem that is convex, as it is written, on non-negative functions that are m times differentiable. So we can use the model we have presented before. Okay? And in particular, now we can discretize it because we have a dense set of, so we have an equality over a dense set, and this is where you can apply approximation theory. So this result is if you want, the classical result that I showed before spelled out. If you have your function that is, if you constrain your function to be 0 over a set of points that are well distributed in your set, then you can see that if you have a number of points that is in the order of epsilon d over m, your function cannot be larger than epsilon in the whole set. And so this is a way to control the behavior in a set, just considering only a few points. And why this works? Well, because u is m times differentiable, so it has some rigidity, and you use it to control the behavior everywhere. We apply this result to the function u that is h minus c minus f. This should be 0 by construction, and it is m times differentiable. So now we can use this result. And to conclude, so we just rewrote here the problem, but we have still to do the optimization over non-negative function. How do we do it? Well, here we apply the model we have seen before. And if you just use the translation, so this was a convex problem, we put the representation we had before inside, and we obtain this SDP problem. Now you can solve it with a complexity that is n to power 3.5, where n is the number of constraints that you have here. So, do we find the global minimum in the end? If we put all the things together. So, this result is spelled out for the case where the function is Sobolev. So, we are achieving here the optimal rate for Sobolev functions. It is a bit different from when the case where the function is only m times differentiable. So, we see that we achieve the distance between the minimum C star, that is the minimum of the function h, and the result of our algorithm is of order epsilon if we dimension our problem choosing n in the order of epsilon minus d over m minus d over 2. So with respect to the optimal rate, we are losing this minus 2 here. So what does it mean? It means that we can find, so now we choose n of this order, we run the SDP we have seen before, and we achieve, so the global optimum with the cost in terms of computational complexity that is 3.5, so that is 3.5 times n, that is d over m minus d over 2. So if you want, we have a result that in spirits achieve the same trade-offs of the result, what we would expect in the optimal rate. So a rate that become dimension independent when M is big enough. For example, here, if M is larger than D over 2, than 2D, you can escape the curse of dimensionality, and your algorithm will require only epsilon minus 3 to achieve the global optimum. Of course, there are constants here. The constants are unavoidable in the general case and are in the order of D factorial. You cannot avoid them. I mean, you can build cases if you take a function that changes over the hypercube where you cannot avoid this constant, but it's reasonable because otherwise we could solve NP problems in a polynomial time. Well, that's it. So actually we have seen a general technique here. You take a problem that depends, so it is an optimization over functions and with possibly a dense set of inequalities. You transform the inequalities into equality by adding a non-negative function. You subsample the non-negative the set of inequalities and you use the PSD model. You can apply the same technique to many problems that can be written in this way, like optimal transport, some cases of optimal control, and in particular on probability representation and Bayesian inference. But I will not talk. So we worked a bit on those topics already, but I will not talk about it today. And so, one word. So this model is not new. For many of you, you already know it, and you worked on it for more than 20 years, I would say. This was initiated by Lasserre in 2000, and it was the case where you can consider this as a sum of square of polynomials. So if you take your set of nonlinearities as polynomials. We discovered this later, while the algorithm was obtained, and it is interesting because our viewpoint is different. So, if you want to express it with 2 words, is that the SOS polynomial approach is algebraic in the sense that it does not obtain the solution until the problem is big enough that the solution is exact. Here, instead, we obtain an approximation rate. So, given a budget of computation or an error that we want to achieve epsilon, we dimension the problem such that we can achieve error epsilon. And what we gain from the fact that we have more functions is what you gain when you go from the Zariski topology to the Euclidean topology. So you can obtain geometric conditions. So when a function can be represented in this form, well, we obtain a concrete geometric condition that allows this. So this, yeah, that's it. I finished. Yeah.
Many thanks. Many thanks, Ale, for this enlightening talk. We have we're running a little bit out of time, but maybe we can allow a short question to Ale from the audience. Milan?
So your rate was epsilon to the minus d over m. Yes. So what is m equal to infinity? What happens then?
So in this case, you are talking about analytic function So you are talking about analytic function or
polynomial.
Yeah, or polynomials. So in this case, the rate becomes log 1 over epsilon.
Okay, so the epsilon doesn't disappear completely.
Doesn't disappear,
right.
No.
Okay, okay.
No, because you still achieve it at infinity. I mean, unless you're lucky, your function is a kind of SOS, a sum of squares of Sobolev functions, but it could be not the case.
Thank you.
Thanks again, Ale.
And so we are now moving on to the CS territory. So after a speaker from function analysis and a speaker in the optimization for machine learning community, we'll have Jan Křetínský, who's a rising star in the formal systems community. So he received his PhD from the Czech Republic and done a postdoc in Vienna, and now works at the Technical University of Munich. And hopefully he will return to the Czech Republic because he has recently received a multi-million euro grant. But he would tell you all about that if that works out.
Thank you very much. Welcome everyone, and thanks for inviting me, and thanks for the opportunity to talk about a bit of work that I am interested in, and that is a bit, I would say, different from the previous talks. It's maybe more overlapping with the trustworthiness that is going to also be a topic of the session in the afternoon. But it's also about how math can help here. So I'm going to talk about an interesting intersection of AI and verification and how they can help each other, and sketch a few challenges as well as some examples showing directions how we could possibly overcome them. If you don't mind, I will try to actually have it very non-technical and high level. And if you have any questions also throughout the talk, don't hesitate to interrupt me. So let me start with something that we are all very much aware of, and that is obviously AI having tons of applications. And let's say you already have cool learning algorithms, you have all the math to make the tools work well. You have all the tools that learn for all these great applications, and you're very happy about them. So in some sense, this could seem to be the end of the story, but actually it's just the beginning of the next story, which is whenever you apply AI in any of these areas, and it doesn't really have to be processing of medical data or controlling medical devices. It's pretty clear that humans could be endangered, and of course not only just the traditional human safety in the physical sense of cyber-physical devices, but of course AI is applied in financial and legal matters and so on. So certainly you want to ensure that AI works well. What does that mean? Well, it doesn't really necessarily mean just that you approximate some function reasonably well. First of all, it of course means that there is some correctness of the function that you have learned. So that may mean not that you're close, but that in on certain types of inputs you actually make no error, right? So it's just not that you're probably quite close, but you're simply not hitting the car in front of you, or that you're simply are fair with respect to some well-defined criteria when you are judging whether someone will get the loan. But this is still not the end of the story. Suppose that you even say that we even, it's not even clear what the correctness actually means, so we will get to that later on. But say that you even prove mathematically clearly that the function is approximated well. Still, this is not the end of the story. You have to convince others that you have done so. And you will not do that using the proof. You will have to first obtain certification from the authorities. So you'll actually have to convince people who are saying that this has been developed in accordance to the techniques that are considered okay. So you need to get an official stamp on it, and a proof is a helpful weapon, but this is not the end of the story. So you have to convince these certifying authorities, and this is still not the end of the story. You also have to convince the users and the people around you who are going to be affected by the decisions made by AI that actually the function that you are returning is the right one. So in particular, you need to make people believe that your system is indeed correct and is doing the right thing. All right, so for that, verification comes to the call to arms. Verification is or the traditional task of verification is proving that systems are doing what they should be doing. So it should feel home well with correctness. No one feels at home with explainability yet, so let me show that verification can possibly help here. Now, the task is very hard, very new, and we need help with that. Fortunately, there is someone who can help us in verifying AI, and that is, who could that be? Well, as soon as we realize that verification is just another possible application of AI, we may try to call AI to help us verify AI. So with a pinch of salt, neural networks could be verifying other neural networks. Of course, the fun part is how to ensure trust in a neural network using another neural network that you don't trust either. All right, so let me see whether we can do anything about this. So what is verification? So many of you have not probably heard the word, or not, and at least not very frequently. It's a technique that has been applied very successfully in hardware systems in recent decades, also in software systems, cyber-physical systems. Essentially, the deal is you get the system, you get a property, and verification is here to tell you whether the property is satisfied or not. Possibly giving you some additional information about, for instance, how to ensure the property, or if the property doesn't hold, what is the problem? What is the, for instance, the bug trace? Now, let me give you an example of something that we all know from textbooks. Say, from operating systems domain, you want to have a mutual exclusion algorithm, then this is quite a classic task, but it has been proven by experience to be pretty hard to achieve in various complex settings, distributed settings and so on. And there have been so many solutions that were wrong. And then, of course, if humans' lives don't depend on it, then who cares? But sometimes they do, and then you want to check that your solution is correct. And then one way, one approach is to actually specify exactly what are the properties that you want to achieve. In this case, could be that the two agents are not accessing maybe the shared resource at the same time, but at the same time you're not really they're not deadlocking. There is some progress. There is some fairness, and so on. So there is a well-defined system, there is a well-defined set of properties, and then it's about finding efficient algorithms that decide whether the properties are satisfied. Okay? Now we're getting into much more interesting setting where on the one hand we have a well-defined system, but on the other hand we don't really have a well-defined set of properties. We don't really even know what that means. Exactly, that say a neural network is recognizing well all the objects in the camera view. What does that really mean? I mean, in the end, there is a well-defined objective, which is we don't want to hit the car, right? If we're, using it on autonomous driving domain, or we don't want the patient to die because of malfunctioning device. But that's just, too far away from the technicalities of what the AI is actually what kind of task the AI is actually performing. And for that reason, people have been looking at various proxies. For instance, there is this idea of neural networks should be robust. So what does that mean? If you perturb an input, then the result of the neural network should be the same. So we all know these adversarial examples when whatever kind of, elephant is then you change 3 bits in a large picture, and then it classifies as zebra, right? Which is obviously something that is very funny, can be also very dangerous. And it's also clear that this property cannot really hold. Well, obviously, for all the images that are exactly really on the boundary of the two classes, Of course, at this point, the function is not the approximation is not robust no matter what you do, because the actual original function is not robust. So what does that even mean to have something that is doing the job, right? So we are in a situation where we're not really approximating a function and we would like to be close to it, but we're in a situation where we really don't know what our function is, and people might even have disputes about what the function is, and then, okay, what is the desirable property? You can also do things such as range analysis, which is basically the neural network is not giving me some funny outputs, something that is completely nonsense. But this is more of a sanity check. It's not really checking that it's returning the numbers it should. So again, these are very incomplete specifications. So even if you are able to check any of those, then this doesn't really say that much about how well you learned and whether you can really rely on this. So what we also need to seek for is mathematical phrasing, mathematical understanding of correctness. What does it even mean for functions to be well approximating other functions in the setting? And people who are not actually trained in formal thinking and mathematics, who are actually just setting up the standards, they will not help us. It's up to us, okay? We are not experts either, right? I mean, no one is, but we have to do something about that. And we have to figure out the formal side of it. And this is not coming from the regulations. They don't know how to do that. And this is what, of course, all the car companies are also quite afraid of. Right? I have some collaborations, for instance, with Audi, and then they are promising that we will deliver this and we will deliver that, autonomous driving in a couple of years. Well, I mean, these things are still in the way, and they're working hard on this, right? But I cannot say much more, but you get your picture, right? Okay, and say we already have the property we want to check. Of course, we're getting into the trouble of checking that the properties hold. So you have a well-defined system. That's good. But the traditional verification is only able to help or to prove properties of systems that are well structured in the following sense. If you have, say, a program, then you have a lot of variables. They have their meaning in the head of the programmer. There are invariants of cycles that maybe no one really writes down explicitly, but it's there. Is there in the background, and then there is a way of maybe automated provers figuring out how to proceed and how to prove correctness of programs. There is a lot of structure. Here what we see is a large mess, right? I mean, it's just like neurons connected with weird numbers. Of course there is structure. If there was no structure, it wouldn't be solving our problem. But it's exactly because we don't understand the problem, then we call for machine learning to solve it for us. We get a solution, and of course the deal is we don't understand the solution. That's why it's actually so good, right? I mean, this is a trade-off. If we could solve the problem easily, we would do that using a program. We wouldn't have to learn it. And where is now the structure, right? So for instance, let me give you a more concrete example. So in verification, one of the key instruments is abstraction, which is actually a key instrument of human knowledge anyway, to throw away pieces of information that are not so relevant, to keep the problem sort of simple enough. Now, how do you do that in standard verification? Well, you figure out that different states of the program may be essentially equivalent. Maybe they differ in the value of one certain variable that is not really so important for the correctness of your program. And then you can reason about the simplified program, and that's how you can tame the curse of dimensionality, so-called in this area called state space explosion problem. But we don't really know anything about the neural networks. How can we figure out that two neurons are essentially doing the same thing by not examining the network but directly looking at it, right, without doing much of a computation? Well, I will get to some ideas later. All right, so we are in a setting where we don't really know exactly what our problem is. And if we have the problem defined, then we are in a setting where we have not too many ideas how to approach it using the standard techniques. And this is also the situation of people who are approaching it from, say, the machine learning area. They are looking at the robustness analysis of their neural networks and so on. But again, I mean, there are the two drawbacks. Robustness may not be the thing that you want to prove, and even if it is, then what they're doing is they're proving it with high probability or on areas that have at least some measure, but I mean, maybe not in the one specific example that may still happen, and therefore this is not really certifiable because it's still possible that things like that happen. All right. So this is one part of the story, the correctness. The other part of the story is, even if you have now a correct system, even a provably correct one, then you are supposed to, according to the standards that are already a couple of years old, both in the European Union and US, you're supposed to make the system explainable. If you try to search for what that means, you learn very useful information such as it means understandability by human. Well, at least we know that by human, but by whom? We don't even know that, right? I mean, is that the domain expert who designed the solution? Is that the people who run the service? Is it even just the customer? Should the customer understand it? And there are of course legal battles about various interpretations of these regulations. I'm going to stay away from that. But what is interesting is it then supposed to be understandable using the domain knowledge? Often the people who are actually programming or learning a solution to some problem, they're not even domain experts, right? They don't even, I mean, when they get a solution, they have no clue whether this is a correct one or not, because they actually don't even understand the problem, right? I mean, are these people supposed to understand it, or do I have to be a domain expert in order to understand it? This is also not very clear. And let me just give you a glimpse at what some people do in explainability. And of course, usually it depends now on what are you explaining. So on the one hand, we have something that is still quite manageable, which is concrete decisions of AI-based systems. Okay, so you have a neural network that says, no, you don't get the loan. Now, of course, you're interested in, okay, why? Okay, I'm earning enough, why? And then people say, okay, well, maybe we could give explanations in terms of counterfactuals, meaning what has to be different in order to receive the loan. Okay, so of course this is easy, right? Or easy in the sense of we know what to do. Now comes all the math that takes the function and sees, okay, what is the minimum change so that we actually get an answer in the other class. Okay, and this is then, I mean, if you want to get the least possible change, this is when the optimization comes into place and all the cool math can take place because we already know what to do. On the other side of the spectrum, we are supposed to even explain the systems. What the hell means that? No one really knows. Of course, we have some understanding of the systems, maybe in terms of rules. So, I mean, the traditional rule-based systems like programs, for instance, we have maybe some domain knowledge, so we know, okay, we probably, when we are right behind another car, we probably shouldn't accelerate because we would be hitting it, but that's not saying it all, right? And there's a lot, I mean, if we understood the system in terms of rules, we wouldn't have to call for learning. Now we have learning there because there are a couple of things that we don't understand, we have to learn them, and then we need to now combine the sort of symbolic rule-based things with the learned systems. And of course, neurosymbolic topics are fancy these days. So I mean, there are some ideas how to proceed, but the whole area is still trying to find the vague directions and is very unclear. In the middle of it, there is maybe a story that I want to zoom in on in a minute or two, or for a minute or two, which is representation of controllers. So what do I mean by that? Maybe you have a cyber-physical system, could be a robot moving somewhere, and then it's supposed to make some decisions so that it behaves well, say in interaction with humans. And now maybe what we could also do is not to forget about the rest of the AI. So it's all about neural networks these days because they can be trained well, as opposed to, say, for instance, decision trees, right? I mean, this is who would use decision trees these days when you can have a neural network which is much faster. I mean, it's faster trained, much more accurate. But, well, there are other advantages, or there are other points than just approximating well, and that is decision trees, for instance, are more interpretable. And they have, I mean, this is something that people use when you get your car repaired. I mean, this is what the people in the repair facility are using. They understand it, right? I mean, is the engine turning on or not? If not, I mean, is then, I mean, oil dripping from the engine or whatever? And if yes, okay, what should I do next, right? I mean, this is something that everyone understands. So let me give you a brief example of a controller, right? This is a controller. Okay, so you probably don't really see it. It's megabytes of lines. If you zoom in a bit, I mean, this is a control that for each state of the system tells you which actions are safe. What is this? I mean, this is many thousand lines of these, actually just describing what you can do in a flat with 10 rooms, 2 heaters, and then, I mean, sensor in each room. Now, what are you supposed to do when you can turn the heater on and this one off and so on? Very, very complex, right? What you would rather like to do is to actually distill the information, but not into another neural network or anything. But you would like to use some data structure that you understand. Okay, first try. If you know about them, binary decision diagrams, a big thing in many areas to represent complexly Boolean functions. Not really. Okay, maybe something else. Maybe you actually need to employ learning to figure out what is deep down there. And then you actually, it turns out that to obtain a safe controller, you can actually simply do the following. If the temperature in that room is low, then you turn the heater on, and the same for the other one, and that's basically it. And you obtain a safe controller. And of course, you don't even need the other sensors, and all that you learned is actually in the end quite trivial, right? I mean, this is an extreme case, but I mean, you save a lot, and maybe this is still an extreme case, as I said, but you really want to see what the controller is really doing. Maybe let me give you very briefly another example. A very simplified system for keeping distance between the cars. If you create a table, what to do in each state of the system. I mean, you can't really read it, you can't really analyze it, you can't verify it, it's just too large. Now you can create a decision tree. Now, is this understandable or not? Now, what is this? I mean, you have seen quite fancy formulae in the previous talks, but still, I mean, is this understandable or not? Well, it really depends. If you have the domain knowledge, like the kinematics equations, it's pretty easy to actually figure out that these turn out to be simply the worst case distance to hit the car. If you're accelerating, then you take the worst case overall, what the other car can do, and this is then the critical distance, which then makes a lot of sense. Right? It didn't make it here, right? So what we have to do is, of course, to merge the approach that learns maybe these interpretable data structures also with something that learns sense out of expressions, right? Which is also what people do, and so there are ways how to approach this problem. So let me then summarize. Let me just skip over that. That many of the approaches that are appearing in the field are of the form, okay, we don't know what to do, we call learning to our aid. Of course, learning is not reliable, so what we do is we observe the system for a while, maybe observe a couple of runs of a program, and then we figure out what the invariant of the program might be, and then we can check it, right? The guess can be wrong, that's okay. Then we go on searching, right? But you can use AI to actually then provably get the properties of your system. Or maybe you observe, if you observe a neural network, you observe the behavior of some neurons and you make a hypothesis, you make a guess that maybe actually they are doing something. And then once you have that guess, then it's way easier to prove it than if you don't even have the guess. So it also has, I mean, in this area, it is vital to bring also the methods, the wild methods, wild unreliable methods of machine learning and the classical math together to pull one rope in one direction. And let me then just conclude. Verification as well as math are to be here in a dialogue with AI and not one directional application or analysis. They should help each other, and we have seen on a couple of examples that such things are possible and happening over the past few years. So I wish us good luck in pursuing this. Thank you very much.
One question, maybe. Cordelia. I'll run with the mic.
Which of these different techniques will give us the most gain? I guess these decision trees, they're probably very nice for specific applications, but probably not generalizable to any kind of approaches. So anyway, what is your intuition? I mean, like, where are we going to be in 5 years? Do you have any intuition where this will be heading and what is most promising? I mean, if you would want to have one big bet, what would be your take on it?
Let me comment on exactly what you mentioned, the decision trees, and in 5 years. Well, firstly, in 5 years, I think we will move a bit, but we will still be looking around. It takes some time. It's already a couple of years that actually I learned that very recently that Hinton suggested, Geoffrey Hinton, the guy who got the sort of Nobel Prize, right, for neural networks, the Turing Prize. Then he suggested we should be working with decision trees that in their nodes have neural networks, so that we understand the overall structure of decision, and then the subroutines that we don't understand should be actually dealt with the neural networks, because I mean that's where we need the learning. If we have something like we had, I mean it's already gone. I mean the funny formula. That's the thing. Maybe that's the thing that you don't understand. You need a neural network there, but then there is some magic thing that tells you what the distance should be. And then you understand, okay, I probably should not be too close. What that means is hard to compute. The neural network does it for me. But I understand it in the context of the whole decision making. So the key is, it's not going to be decision trees, but at the very least, it's going to be a combination of, say, decision trees and neural networks. We have already seen more complex predicates, but there have to be also other ones. So the thing is, we will have to combine this into new models. I mean, that model has been suggested a couple of years ago. No one is still learning it. No one probably knows how to do that well. But this is a model that could be much helpful. It's there for a couple of years suggested. People are still not learning it because they don't know how. And we need these types of models, of course, together with the adequate learning procedures and the math that tells us how to operate with them. And only then we can hope both for understandability and accurateness. So I would start with that one. It's there for already a couple of years. People agree this could be a good thing, and we still don't know how. So maybe we need to find the right subclass, the right tweaks. And I would start with that one. And if in 5 years we don't know for at least that single thing how to do that, I would be already very happy. I'd be also happy to take questions offline.
Maybe a last quick question. So, is it possible to display the slides and just go back just after just before the conclusion, please? You described a protocol for explainability and understanding of neural networks, and I was wondering if it is automatized. I don't understand where human is and where machine is.
Mm-hmm. All right, so of course this is a bit of a process. So what we are actually having is a tool that, for instance...
Before, yeah.
Yeah, so for many of these things, we do have semi-automated to automated procedures already. Right? So for instance, for seeking invariance based on runs of programs, this is something that people have been working on, or many people have been working on for already, I would say, 6 years or so. So there are already quite some tools. For producing these trees, we already also have a tool that actually does quite a bit. But in order to be very powerful and figure out these more complex things, such as these predicates, there needs to be a bit of intervention of the human. For instance, we need, at the moment, we need that you enter the kinematics equations, and then we are blindly searching for these expressions. Of course, if we had better guidance, it would be better. So, I mean, it's semi-automatic, and there is, of course, vision to make it fully automated, but it will always depend on some inputs of the human, at least optionally, because whenever you know something, you should not let machine learning figure it out on its own. You should enter that information. Of course, this is also something that people still don't know well. I mean, how to merge rule-based systems and learning-based systems. If you have prior knowledge, how to efficiently encode it into your mechanism. This is something that needs some time, but I mean there are already some automated procedures that deliver results according to this scheme. Thanks for the questions.
Thanks so much for the questions. And so now the final speaker of the day will be Thibaut. Thibaut works in one of the groups you have heard about from Professor Šibec yesterday as the sort of highlights of the Czech AI scene with Professor Josef Urban on proof assistants. So proof assistants are really the core of the, or the holy grail of the computer science, undecidable and yet very desirable, and Thibaut will tell us all about them. Thank you.
So hello everyone. So my talk will be focused a bit more on the mathematical side of verification. And proof assistants are actually the software that does the verification. So the talk is divided in 3 parts. The first part is we will answer the question, what is a proof assistant? And then we will show what they are useful for. And then we will show how we are improving proof assistants. So first, what is a proof assistant? We have to ask, what is a proof? So at the beginning of the 20th century, there was this crisis in mathematics. The mathematicians were exactly asking this question. What is a proof? So some people wrote a book and they're trying to define what is a proof. And this book is called Principia Mathematica, and it was authored by Whitehead and Russell's famous logicians at the beginning of this century. And what is inside this book is set theory. So set theory is one of the foundations of mathematics, and it contains axioms, so some formulas that we are assuming to be true, and it contains rules. The rules are used to, from the axioms, you can derive new theorems from these rules. So there are the first axiom, for example, could be the Prairie Axioms. So it says that if you have two sets, you can construct a set that contains exactly these two sets. There is also an infinity axiom that says there exists a set that is infinite, and so on. And you have like a finite list of these axioms, and you have a finite list of rules. For example, you have modus ponens. Like if you have A and A implies B, you can deduce B. A and B can be any formula. And you have also, you can instantiate. So if you have a for all x, P of x, you can replace x by any term T. So now we can construct a proof. We have our axioms, like 3 axioms at the top, and we have a conjecture we want to prove, and we can combine the rules with the axiom to produce lemmas, and we can then maybe produce a conjecture, and once we have derived the conjecture, we have a proof of that conjecture. So that's exactly what it means to be a proof. And contrary to any textbooks or mathematical textbooks, there is no unweaving here. Everything is programmatically defined. There is nothing left. No details missing. So, in summary, what is a proof assistance? So, a proof assistance is a software that defines a foundation. So here we have seen set theory, but you can also start with other type of foundation, such as type theory. And it verifies proofs, and it helps write formal proof faster, and that's what we are going to see later. So now, what is it useful for? So the first example I want to show you is the 4-color theorems. So you have a map, and someone tries to color the map, and he realizes that you can always do it with at most 4 colors. So the map has this property that no 2 countries should have, that border each other should have the same color. And that's surprising that you need only 4 colors maximum. And this was proved by Apple and Aiken in 1976. But there was a big part of the proof that involved checking many cases by a program. And we could not, the mathematicians are very skeptical when there's a proof generated by a program. So we had to use proof assistance. So Georges Gontier used proof assistance to verify that the programs are actually correct. And so that's for a useful case in mathematics, so that there is no doubt left in the proof of the theorem. In software, I give another example. One can verify, implement a verified C compiler and verify that this corresponds to the specification. And this involves translating the manual, the C manual, into some formal statements, so that's a hard job. And it also involves verifying that it actually respects the code that is translated or compiled, actually verifies the specification. And informally, this means that the compiler is guaranteed to behave as expected. So the last part of my talk is about how are we improving proof assistance. And I will mention 3 challenges. The first challenge is auto-formalization. So we would like to have the proof assistant be stronger. So we will like it to be able to read from, for example, the archive or from the specification and automatically translate the English text into formulas, basically. And there are many issues with this process that we are trying to solve. The first one is you have ambiguous formula. So if you see this first formula, cos x squared x plus sine x squared x equal 1, famous identity, how is it ambiguous? Well, if you have a machine, I might think that you are applying cosinus twice, because that's the notation for repeated application of cosinus. So you would want to have the exception in this case that it is a notation. Or you could think, what is x? X, is it a complex number or a real number? So I have many choices here. So all these choices have to be inferred automatically and have to be correct with respect to the context in which the proof was made. There could be errors in the proof, and there could be gaps in the proofs, and that's where the second challenge comes in, that we would like to, for the gap in the proofs, we would like to be able to complete these gaps automatically. And if there are errors, we would like to fix them. Maybe they are fixable. And so the second challenge, we are going back to these pictures of derivation, and we are trying to derive the conjecture automatically. This is called automated deduction. And we have many choices in which we are combining the axioms. And usually, we can think of this problem as a path-finding algorithm. So we are trying to find a path from the axioms to the conjecture, and the graph is made by the rules. And we can apply all kinds of search algorithms like A* or MCTS, and we can guide this search by machine learning algorithm. So the last challenge is automated conjecturing. So I just give one example here. I want to prove that if there is a function f, such as f is continuous but not derivable. What I will do is I will conjecture that a particular function is continuous and derivable, and this is, for example, the absolute value of x. So how did I get to this conjecture? Well, I know it from experience. I might have drawn pictures. All this kind of reasoning, which is not deductive reasoning, but kind of inductive reasoning, is not covered by the previous approach. So we would like to also have this previous approach. So I just show an example here for software that I've developed. It's a self-learning software that, given a sequence, returns a program that generates that sequence. So if you give it a sequence of prime numbers, this is a Python program it generates. And this was all done by self-learning without any human knowledge to start with. And this is a nice example of something that is kind of explainable. It starts with machine learning. Behind this, there's a lot of machine learning. The machine learning is selecting the next token in the writing the proof, not the proof, well, could think of it as a proof, the program. And in the end, you get a program that you can interpret and is also explainable. And I can tell you what this program is. It's actually computing the Fermat primality test. So it's, there's some, to compute the prime, it does some approximation, and it's only correct up to until 341. So you would like to, if you would prove now that this program is correct, then you would see that it's wrong, and you would find another program. But it's almost correct. So in the end, I would like to conclude by saying that proof assistants verify proofs beyond the shadow of a doubt. So we are really sure about the proofs we get. So the only thing we need to verify is the proof assistants themselves. And why we are sure about why the proof assistants are correct is because they have a very small kernel, so a very few lines of code, and we can verify manually that they are correct. In the end, we are improving them so that they can read the archive by disambiguating formulas, and they can prove more and more theorems by using a combination of deduction-based and induction-based reasoning techniques. Thank you.
Well, thank you. It's very interesting. But is it science fiction to think that you will have a program verifying the validity of an article, or can we really hope for that?
A validity of
an article. So
an
you just said that you are able to say if an archive article is correct or not. So as an editor, I'm interested by your discovery.
Yeah, this is just the beginning, and we are trying to, for example, maybe like we would like to start this project with doing it for example, Principia Mathematica, which is already very close to a formal language. So if you take any article in the archive, it's probably impossible at the moment because there's so many assumptions. And
yeah, I understand. But what is your reason, to your opinion, of this?
I think it's could be helpful, for example, for the conjecturing challenge. So we could take this formalization idea and just, for example, at the moment, just take some formulas, and they could be plugged in as conjectures in the. So there could be an interrelation between these three different parts. So I think it's already possible to read some part of the archive and use this to improve the power of your deductive system by just picking up formulas. That could be interesting.
Right, so the fundamental challenges are really in the sort of undecidability of the proof assistant itself, right? The machine learning to get you from the archive PDF to the sort of a formal write-up in which would be the input to the proof assistant is in some ways like easy, and there are no like theoretical sort of barriers to that. But then sort of for the proof assistant, you have lots of sort of impossibility results in theoretical computer science. So sort of you would know that you will never have a perfect system for that. But you can download packages which are surprisingly powerful, right? Very powerful packages which you make it possible, if not easy, to prove sort of non-trivial things or verify non-trivial proofs. Any further questions? I have checked the Slido a minute ago, and I think that we had no questions from the online participants. So if there are no further questions from the room, I would like to thank all the speakers again, and also the audience for the participation. Thanks so much. There is a coffee break upstairs, in case you haven't been.
Dear guests, I would like to invite you to the coffee break upstairs, and also
computers are quite good at this. And they want like sound intermediaries and get the yeah, like it was not the truth, but like
Je ne me sers jamais de Windows, je sais pas comment on débranche une clé.
Je sais pas. T'as pas une, un truc USB en bas normalement? Moi non plus, j'ai pas Windows.
Je crois que je vais la débrancher comme ça. Ah. Éjecter.
C'est pas ton PC?
Si, mais d'habitude je travaille sous Linux.
D'accord. Tu mets en Windows, c'est quand tu fais l'installation?
only have this big mic, right? You don't have any wearable mic. Attach it.
so that's typing, but there are some waves and sending.
I will say a little bit logistics before we start.
Okay, good.
Okay, in a couple of minutes we will just begin. Thank you. So maybe I will use this time, and meanwhile I would like to invite all of you to really participate at the tour, guided tour, which will be held today at 4 o'clock here downstairs in testbed for Industry 4.0 with various robotics demonstrators. It will be for 30 minutes, one floor. We have 2 floors, so 1 hour you can spend with some nice demonstrations. For tomorrow, there is a special visit to Valeo Research Center. So you are also invited. There is limited capacity, but we will be happy if you join us. It starts at 9:30, and it's like, let's say, 50 minutes from here if you go by the traffic, public traffic. And you can let us know at the registration desk to the young lady downstairs, or just simply use the link at our website /tours. There you can also see some more details about these tours. Thank you very much and enjoy the rest of the day.
Thank you very much, Eva. So my name is Josef Civic, and I'll be co-chairing with Nicola this robotics session. Just before we start, I want to highly recommend both the tours. So the one which will be here on the testbed, you can do it after the workshop. And the one at Valeo, this is about autonomous driving. So you can really see like a top-notch facilities for autonomous driving. I very highly recommend it. So the next session will be about robotics. We have a very exciting lineup of 4 talks in this session. Again, we'll have 2 Czech and 2 French speakers. And the first speaker in this session is Nicola Manzart. We are really pleased to have him here today. He is a senior researcher at CNRS in LAS in Toulouse. Among his achievements, he received a bronze medal from CNRS, and he's done a lot of exciting work on robotics. So today he's going to talk about robot motion learning and optimizing. Nicola, thank you very much. The stage is yours.
Thank you for the introduction. So I'm doing mostly leg robotics. So I'm trying to make robots with legs and arms move in the world as well as we are doing. And this is a very exciting moment for our research because some robots start to walk. So it's a longer, the research started long ago, like 50 years ago, and we only see the first real results. And in particular, quadruped robots are now working very well, and we see more and more quadruped robots flourishing around the world. Among these quadruped robots, maybe the 2 most well-known, or the 2 first one, are Spot on the left and Animal on the right. So Spot, the American one, and Animal, the Swiss one. And what is strange to me is that these two robots are approaching the problem with very different ways. Spot is using trajectory optimization, so model predictive control, while Animal is using reinforcement learning, so policy optimization. And basically both obtain similar results at the same time. So I will discuss that today, but maybe mostly my talk would be about what is the mathematics to make robot move. But maybe before entering this mathematics, I would like to explain you a little bit what I found appealing, exciting in this research. So first reason why studying robots at work is interesting is that by itself, it's interesting to have robots with legs. There is very different ways of navigating in the real world. And of course, if you are in the flat floor, you want to put wheels. That's the most efficient, and there is no discussion to that. But very soon, you would be in environments where wheels are not enough. And if you have enough space, or if you don't need a big robot, then 4 legs is very likely the best way of doing. It's very efficient and it's very stable. And that's what currently is working. First, because we have 4 legs, but also because quadruped robots have no feet, means no motor, low in the chain, and that's also much more efficient. If you want to have increased safety, I don't know, maybe because you are very big robots, or you want to cut trees, you want to act in a nuclear plant, maybe you would need a third pair of legs, 6 legs, which is less efficient because the legs collide, so you cannot go as fast as for quadruped robots, but then maybe you have increased safety. If you have a constrained range, for example, if you want to clean this room, likely a quadruped robot is too big, it would be too large, and then you need a biped. Biped robotics is not mature yet. Biped robots tend to fall, and when they fall, they tend to break. But well, they are very long-term solution if we want to go everywhere where human can move. Mixed solution like this centaur robot with 4 legs, with wheels at the foot and with arms is also very appealing. And clearly, if you have a lot of space, a centaur robot seems a very good solution, but you very likely won't be able to act in this room. And in general, you can find morphology dedicated to your task. So going with legs or with wheels or with 4 legs a priori is a stupid idea. And Shaft was a company in Japan with very successful robots that was eaten by Google and kind of disappeared. That's too bad. But they were relaxing this animal-inspired morphology with these biped robots that had 2 elbows per arm and 2 knees per legs, and that was much more efficient. And with this very small robot that has absolutely no knees and is using a linear actuator for retracting the legs. So morphology is not something that is defined a priori. A second reason why locomotion is very appealing is that it's a representative problem of many other motion problems in robotics. And in particular, locomotion is a dual problem to manipulation. In both cases, you want to move an object by applying forces on this object. In manipulation, the object is not yourself, and in locomotion, the object is yourself. So for me, that's the main reason why it is interesting. And in that sense, locomotion is one of the very hard challenges of robotics. And robotics is known as being one of the hard challenges in artificial intelligence. And it is a challenging problem because first, we have delayed reward. So when you push a robot standing still, it would quickly discover that moving the arms, waving the arms, created angular momentum that helps the center of mass to come back to a stable position. But for finding that he has to raise a foot and move it forward and making a step, that only provide a reward long after the start of the move. And if you don't move the foot at the right place at the right time, then the robot still falls and the reward is still awful. Second reason is that we have a lot of constraints in leg robotics. We have a lot of collision, a lot of torque limits. The robot is underactuated. He has limited field of view. So, and all that constraints are not negotiable. If you have a joint limit, you cannot pass the joint limit, otherwise the robot is broken. And we need to be able to handle these constraints. And that's, for me, the only path to something that we could certify in terms of the robot mobility. And finally, what we really want to have in locomotion is apply some forces on the environment. That's really the key to locomotion, but it's also the key to manipulation. Because only by controlling the forces, you can kind of foresee what would be the motion that would appear later. If you apply the wrong force, then it would lead to the wrong movement, but you will only notice the movement later. So applying the forces is all the key. And when you work with forces, then you make your system very unstable. But in my opinion, it's the only way to go to really obtain first good locomotion and then good manipulation. So that was the why walking. As I said, my talk is about mostly how to walk. For that, we need to understand what is the state of the art, what we did first in the locomotion community to make system work. And currently, what is actually working on existing robots. So the first step that Robotics did is to design some suitable models that would at the same time capture the complexity of the robot and be able to be manipulated by algorithm. And mostly we want models that are linear enough and small dimension so that motion generation algorithm can capture them. And actually we came up with a lot of lot of models. My favorite maybe is the flying potato model. The one that is the most used is likely linear inverted pendulum based, but mostly all of them lead to some algorithms that are easy to manipulate this kind of dimensionality. So dimension is 2 or 3, not too many variables, and mostly linear, so you can work with quadratic programming or this kind of stuff. And then at every given time, the controller needs to decide which force to apply and where to put the foot next. And this fact that the objective only can be captured later in the future implies that we do that by what we call model predictive control. So model predictive control is nicely illustrated by this picture from Colorado University, where you would define the controller of your bot by predicting what would be the effect in a simulated version of yourself. So first you would say, well, if I drive forward, then I would quit the road. If I turn a little bit, I would quit the road again on the other side. If I be smart enough, I would stay on the road, but I want also to be optimum. So I want to decide the future robot trajectory, optimizing an objective function, knowing a set of constraints, basically your current configuration, your current state, your simulator, the evolution model, and other constraints like stay on the road, don't burn your motor, this kind of stuff. So this decision problem is written as a big nonlinear programming model with hard constraints. Where the decision variables are the set of state trajectory in the future and control trajectory in the future. So that's big optimization problem. And we want to solve that not once and blindly apply the trajectory, but each time the robot starts to move, we will have disturbance. The model is not perfect, so we will quit a little bit the trajectory, and we will have to recompute as soon as possible the optimization, the optimal solution. And we are basically mostly interested by U0, so the first control, which we call the optimal policy. So applying that to simple models like linear inverted pendulum models, we obtain the state of the art, and quadruped robots work very nicely with that on the different terrains. And by the way, this is a solo robot that we are designing with Max Planck University and University of New York, which is, I think, a very good open project and a good prototype if you want to start with quadruped robots. So now, the trend and the objective of our community is mostly to scale up this very particular and dedicated model where we put a lot of our intelligence so that we can do predictive control with the whole body of the robot. We would like to compute the optimal policy, but without any specific model, just with the real physical model of the system. Just a quick preview. If we don't have too many degrees of freedom, like if we have here 7 degrees of freedom, doing a pick and place task, so not too difficult, not too many constraints, it's kind of working out of the box. And we obtain good model predictive control behaviors. And a nice point with that is if we disturb the system, it would invent something new. So here, for example, at simulation time, when we program the robot, it only moves forward. And on the robot, when we push it hard enough, it discovers that it can go backward. This kind of generalization is exactly what we expect from this behavior. So here, mostly, I presented an optimization problem and say, well, we want to solve that in real time. So that's mostly optimization. But in the beginning, I said that some robots are going with learning. So what it is? In general, I think both learning and optimization can be understood at the same, solving the same numerical problem. So what we want to solve is this big optimization problem, optimal control problem. And the solution to this problem is a complex geometry, which we can represent here by being either the optimal trajectory or the optimal policy. And clearly, if we have a very efficient way of computing one or the other, we could, either by only choosing the first part of the trajectory, get the vector field, or by integrating the vector field, get the trajectory. But these two objects are only considered by some part of the community. If you are considering the trajectory as your key variable, likely you are doing trajectory optimization and you are likely in the motion planning domain. While if you are considering the vector field, you are doing policy optimization and you are likely in the reinforcement learning domain. And these two domains are not discussing so much together, and in particular, the algorithms are not taking advantage one of the other. Well, most of the time in optimization, in numerical mathematics, when there is two variables that are kind of describing the optimality of one problem, the best algorithms are searching for the two variables at the same time. So I'm mostly coming from trajectory optimization. So for applying this optimal control to the robot, what we need first is very efficient solvers. And we design a solver that is presenting all the good properties that you can expect from the domain. So if you know this keyword, it is multiple shooting, applies the differential dynamic programming principle, using augmented Lagrangian for satisfying strict constraints. We can handle big problems, so like for the quadruped, we need to handle 8,000 variables, and we discover locomotion in 12 iterations. Each iteration costs us 9 milliseconds, so it's enough to be 100 Hertz on the robot. And for the human robot, it's a bigger robot, there is more variables, so we would need 10,000 variables. 18 iterations because biped locomotion is a little bit harder, and we need 13 milliseconds. So all that is enough to be real-time on the robot. Mostly, the main challenge to have that real-time on the robot is to handle the structure of the optimal control problem. These control problems are very big, but they are also very well structured. So this is the KKT matrix of the big problem, and only the blocks are non-zero. The rest is zero. So you see first there is it's plenty of zero, and more than that, it's very, very, very well structured. So it's not only a random sparse problem, it's a sparse structured problem. And even in each block, you still have a lot of zeros. So here the structure is a little bit more difficult. It's coming from the kinematic structure of the robot. But again, there is a lot of structure that we can exploit if we are smart enough. And the last point, the last key point to have that deployed in the robot is that the big nonlinear problem that we are trying to solve, they are typically non-convex. And there is very little hope to make a convex relaxation of them because they are too big for now, at least. So we can only hope to find a local minimum, and sometimes these local minimums are very bad. Like, for example, when you push a robot on the back, a local minimum is to stay still, and it's a good local minimum. While you want to find the global minimum where you raise the foot and capture the fall. And so for that, we are solving this big optimal control problem offline a lot of time, and we are storing the instances of solutions in a neural network. So that at runtime, we can predict what is a fair approximation to the global optimum we are searching, and only let the solver run for some time to find it. So we call that a memory of motion, which is a combination of offline trained memory and online optimal control solver warm start by the memory. And this is an example of a motion library that we implemented, which is available online. We apply this approach on 3 case studies during the European project Memory of Motion that just finished. First, with some behavior on the human robot, Talos, in LAS, for doing some tooling tasks, deburring tasks, polishing tasks, or for walking on flat floor or climbing a stair. We apply that for exoskeleton for paraplegic patients. So here the guy in the exoskeleton, he has no control on the legs, and is able to stably walk. The nurse on the backward is only for stabilization, for safety. And we apply that for quadruped robots, either walking on over some obstacles in Oxford, or climbing stairs in Edinburgh. So here we are mostly using the optimal control with motion planning offline, training a memory, and then the memory is static and is used online for warm starting the solver. And for that, we are combining optimal control, or optimization, nonlinear optimization, with supervised learning. The learning here is supervised, fully supervised by data generated by the motion planner. We are trying now to move to reinforcement learning, so trying to make these 2 steps a complete reinforcement learning algorithm by generating data, feeding a neural network with that, neural network being able to predict the value function, the policy function, but also the optimal trajectories, and then feeding a prediction to the optimization problem so that they can provide better solutions that are, training a better neural network, etc., etc. And then doing reinforcement learning, but by combining optimization and supervised learning. As a conclusion, I think it's a good point that we have robots that are able to work by optimization and other robots that are able to work by learning, because we need to combine both. Optimization, in my opinion, is needed because we want generalization. We want robots that are able to find a new solution, even if they never met this situation at training time. And in that sense, MBC is doing one-shot learning. We absolutely need constraint satisfaction. That's the only road to guarantees in AI, in my opinion. And I have no idea how we could guarantee constraints with current RL approaches. So that to me is really a blocking point. And also in robotics, very often, and in particular with these big robots, you need a lot of numerical accuracy. And the accuracy we get with neural networks is not enough if we don't post-process the result afterward. But we also need learning because we cannot expect globalization at runtime. It's not possible. We don't have the time for that. And more than that, we cannot reinvent the wheel. So we cannot reinvent what is working at runtime. It's too much consuming. And the final remark is that we have both approaches that are mature on the robot at the same time. And it means that mostly the success is not coming from the software, but from another cause that is upward. And I think there is a lot of intelligence in the hardware. Hardware is mature and is making a lot of change. And we are very often underestimating the hardware in robotics. In conclusion, I'm very much in favor of combining learning and optimization, in particular for satisfying constraints. That's my vision of what is hybrid AI, which is the main topic of the ANITI 3IA, so the big Institute for Artificial Intelligence in France, ANITI being the one in Toulouse, where I hold the chair. Thank you very much for your attention.
Thank you very much, Nicola. Are there any questions? I see Patrick.
Thank you, Nicola, for the nice talk. Can you comment on the interplay between simulation and real world for this specific problem of yours in robotics?
Yes. So in motion generation, I like simulation a lot. I think we have a lot of knowledge on the model of the robot, and it's very good to use this model. And in addition to that, all algorithms, whether in trajectory optimization or in policy optimization, they are using a lot of the simulator. So I'm very happy to have a simulator. Our simulators are not good enough, and we are not taking advantage of data coming from the robot to improve the simulators. I know we can get some robustness, and we need robustness, that for sure. And there is some good direction for that. But I think we are lacking a little bit of good direction for bringing back knowledge to the simulation, which, in my opinion, is the only way to expect generalization and good properties. So, of course, there is everything related to adaptive control or calibration in general, which is good, but it's not really making use of the mass of data, and we are lacking a little bit of that, especially to specialize the model in some range of work of the robot, where we know we need some better accuracy. We are lacking of that. Good direction in that.
One more question. We have time for that.
Good morning. Are there any robots constructed for usage in the water, both on surface and below? Thanks.
Yes, that's easy. There is a quadruped robots that are waterproof, And it's for quadruped robots, we don't have too many cables, and now cables can go through the motors. So it's quite easy to make them waterproof. Animal is supposed even to be gas-proof, so that it can evolve in gas, like oil platforms, this kind of stuff, which is more difficult than being waterproof. There is also robots inspired by salamanders in EPFL that are able to have the same locomotion patterns. So even in terms of locomotion patterns, studying movements that are able to work in water and on the ground. So yes, many examples.
Any more questions?
You have Cordelia there?
Cordelia. Last question, then the rest will be offline during lunch.
Yeah, I have one question with respect to the two robots you showed in the beginning. You said one is trained with planning and the other one with learning. Can you just like compare the two, or are they like the functionality equivalent? And if so, I mean,
it's difficult to compare the two. First, because the first one is bosodynamic, so we don't have any publication to really study it in depth. And also because the morphology is very different. I found animal a little bit less efficient. He has big motors on the knee. So the walk is, I find it less smooth than the Spot Mini, which is all the motors in the hip. We see animal is put forward a little bit more on dusty terrain, on a river, on rocks, where there is a little bit less structures, while Spot Mini is a lot on stairs or factories. So it seems to me that maybe Spot Mini is better where the model is a little bit more structured. I guess they're extracting a lot of information from the camera, and then they're applying motion planning on these 3D terrains, while maybe animal is a little bit more less specific and can then go a little bit more everywhere.
right. And so because you said basically the motion-based controller stuff is more generalizable, so this is kind of the opposite.
That's my feeling, yeah. So you have a little bit lesser need of a model with machine learning.
Okay.
And then we see a little bit more generalization capabilities, but a little bit less efficiency, less advanced.
So you're saying more generalizability for the learning base?
Yeah, the learning is able to generalize more, so we can go in a less structured environment. And the motion planning is a little bit less able to generalize, but is then more efficient.
More efficient if the conditions are good, they kind of do better, and then the learning base is more for
But that's
conditions.
a feeling, right? It's not a scientific study.
Okay, thank you.
Thank you very much. Let's thank Nicola again for the wonderful talk. Thank you. So our next speaker in this session is Karla Štěpánová. So Karla is a researcher here at the CIIRC at the Czech Technical University, working in this building. And she's working in robotics, doing some very nice work in imitation learning. I guess she'll be talking about some of that today and building her own team in this area here. Karla, the stage is yours. Thank you very much for coming.
Thank you for a nice introduction. And I would like to also thank everyone for interesting talks yesterday, which were already inspiring part of the talk, as you will see. And today I will talk about verbal and non-verbal communication and how we can use it to control robots or teach them some new tasks. And coming back to yesterday, if there was the question if speech recognition is over, I would say that in this area, the question is a bit more, has it already started? Because if you see the number of papers which are coming recently, every year out, there are like hundreds of them, and it's incredible amount, and it seems like everything is already solved. But when you come to the real world and see what has been done and applied in SMEs or in industry, then it is not there yet. The SMEs and the industrial people, they have high expectations what can be done, which is totally not matching what we are able as researchers to deliver, because the models are not robust, they are not able to have accuracy which we would need for the real application, and they are having, especially these systems which need the communication, they have very big delay, so they are not as useful as they should be, and they are slowing down the industry. But the industry would really love to have some intuitive way how to teach the robots new tasks, because it would enable them to quickly change the tasks and avoid costly reprogramming. Okay. And I will focus on subset of the area, and I will talk about how we can use language and gestures and demonstrations to teach different things, and language in the simple way, which is already used in many devices, in cars and also in industry, can be used just to command the robot. You use some templated actions which are connected to pre-programmed robot motions, and then you are detecting from the language which parameters this action should have. Anyway, if you want that the robot is really able to adapt to new situation and understand what you are meaning, but what you are saying, you need to teach the robot. So for example, you can teach him static properties of the objects, or dynamic, like showing him different actions, naming them, and then asking if it really understood what color is the object, what action was performed, and so on, which is getting more challenging. And when we come to gestures, then similarly, we can use gestures just in a very simple way, where we use them to control the robot and trigger some pre-programmed robot action. And these actions can be either pre-programmed or learned by demonstration. So you can use kinesthetic teaching, some tracked tool, or teleoperation, wearable devices, and so on. But it's always a very restricted area, very restricted set of motions, and given set of templated language or templated gestures. We would like to go further to really make it working. And how you can go further, Josef Šivec will talk about it very soon, is that you can use a lot of instructional videos from which you can learn, but you can also use the real demonstrations, which is the important part, where you are really tracking the device and putting together the demonstrated motions and the positions together with language, because not everything is visible in the camera, in the vision. So you can't see the force which is applied, you can't see properly when things are overlapping, how it is done, if it is screwed 2 or 1 centimeter inside, and so on. All these parameters can be easily specified by language. The problem, of course, is then that you have to synchronize the different sources of information. And when it comes to the learning, then if you want to teach the robot new task and name these tasks, then you can also teach overall body movements. And what we would like, again, is that when you are teaching the robot, you don't need a huge amounts of data, but you can rely only on few demonstrations, on few movements, and it can easily learn, because we don't have infinite data as Google has for the vision data sets and so on. One last thing to mention, it's really important to provide benchmarks which would be suitable also for this embodied reasoning and for this real applications, because we have a lot of benchmarks for vision, we have a lot of benchmarks for speech recognition, but we also try to introduce some benchmarks which would allow to verify how the methods are working actually on the real world data sets. And when coming to the mapping and learning, there is also need for benchmarks which would be explainable, and where you could explain which of the knowledge is already available in the system. Because we have like the amount of new works is so huge that there are coming new algorithms, and they always introduce basically also new data set to show their strengths in the area. And they not always verify them on some unified data sets, which is of course not possible because the data sets are very often not available. So what we have done in the area and where we see the challenges and the discrepancy between the industry expectations and the reality, we have this collaborative robotic workspace where the robots are supposed to work based on the commands given by the user. And in this simple setup, the language can be used to command the robot or set some amount of feedback coming from the system or selecting which task is supposed to be done. And all of this works quite nicely, although it's not maybe as quick as it should be. There are several challenges still coming even from the vision. For example, if you have same type of objects stacked on top of each other, it's difficult to distinguish the borders and so on. But it's getting better. The bigger problem is the synchronization with the knowledge base, which you have to all the time basically update based on the real observations. Because if you see the papers, they often present results on very nice setup where maybe they move some object to change the conditions, but then there is enough time to adapt to the situation, and there is not real cooperation between the human and the robot in the sense that human is moving several pieces and the robot has to react and understand what was the command. Similarly, when it comes to the gestures, I said you can easily use them to operate the robot, and you can learn different types of gesture, either dynamic or static, and then these gestures should be basically recognized in parallel. So you might show a sequence of gestures to specify parameters of the robotic action. You need to show the gesture which is able to specify, for example, end and start of the robot action. And all of this has to be recognized as a sequence which comes together and specifies basically one robot action, which is the challenge again. If you want to show start here, move to the right, place it here, do it and then close the gripper for this size, and in parallel you have language coming with the gestures showing you the task, and then you want to put it to the real robotic platform, it becomes challenging. So, however, even the gesture language can be extended when you can use different like both hands, for example, if you use the context of the situation, and if you take into account that, for example, the similar gesture might have different meaning in different situations and for different people. So all of this, if it is adaptable and can be learned, then the expressiveness of the language, of the gesture language becomes way higher. Here is the one option how the demonstrations together with the language might be combined. So you can imagine that you have some set of instructions, and next to it you have demonstrations where is demonstrated the position and the type of task. And then after processing these two sources of information, you get a description of the robot program, which can be optimized and applied to the robots. So you have some set of tasks, set of constraints on them, set of locations, description of places, and then you can use some planner and scheduling to find the optimal solution when applied to the robot. And the last thing, or one of the last things which I would like to mention is the need for learning and understanding actually the thing. Because all what I mentioned so far was basically you have templates, you know how the word is looking, you have a set of words, you have a set of gestures which you can use. But what if you don't know the word? What if you are supposed to learn the domain where you should work? So there you have to basically learn from just the experience, where you get the linguistic instructions, like description of something, you have some observations, and you have to find the mapping between these two, between the features in the visual world and the words itself, and find the assignment between these two domains. this is very old pre-neural network model. Now all the modalities are basically exchanged for deep neural network, but what stays and what is still difficult is how to find actually the mapping between the domains out of the very simple cases where you would have just image and some simple description, where you would have a realistic environment which is not synchronized, and where you have to deal with the real world. So we have some very promising and good results and impressive outputs of the AI solutions. However, they are still far from being really embodied and working in the real world. The way how to take the recent advances basically in AI, especially the transformers, to the real world, we tried to use the variational autoencoders to teach the robot some simple actions and see how it can learn from few examples. What is the problem here is, of course, that the robot should keep the knowledge of the classes which it already learned before and keep them even when it's learning new classes. And here you can see the performance after just 5 or 20 training samples where the robot has no knowledge before about the movements. And if you use a naive approach, when you would not have some nice generative replay, then of course it forgets the actions which it learned before. So you can use the generative replay to avoid forgetting, and after 5 or 20 samples, it can still then add more and more classes basically to the knowledge. I will skip this, and I will talk about the great vision. So the great vision is that we can integrate these two parts together, that we can have a system which is able to learn new actions, new models just from observations and from demonstrations, and find the simple model of robotic actions. So it learns how to push, it learns robustly how to kick something, and so on. And it can apply it directly as a piece of knowledge when you use the demonstrations and linguistic instructions for more complex tasks. For example, you demonstrate how to set up a furniture, then you don't have to use anymore these pre-learned robot actions, but you are actually using the actions which are in parallel learned. So you are demonstrating the task, and the robot is in parallel improving its knowledge about how pushing works, what you mean by screwing when you say screw it here, and so on. And where we are now, to wrap up, so this is our 1-year-old work, where we, together with people from Imperial College, were putting together linguistic instructions and visual scene, and the neural network is generating sequence of actions which are then applied to the robot. And the model which is able to generate this sequence of action is basically based on mask RCNN, and then it makes some multimodal reasoning, and it's fully end-to-end learning in simulation and then verified in the real world. However, the action sequence is then applied to the real robot, which is having pre-learned action sequences. So still, we are not learning how to move the cube or how to rotate an object, but the loop is closing. And as I was reminded yesterday, there is 1 month old paper from Google who is where they are doing actually very similar thing, where they close the loop, and it made me a bit unhappy yesterday evening because in a week we were supposed to have a 2-week stay of a colleague and to implement exactly this finally in the real world. And what the Google did is that you have a dialogue system and you have a closed loop feedback where you are seeing the scene, and you have a fully learned language model which is actually also generating the inner monologue, like it's thinking what I have to do and deciding, okay, I got the task, so I have to do this, this, and this. So similarly, as I said before, it generates the learned language model, it generates the sequence of actions. However, when you observe the videos which they use and the environment, it's very restricted environment where you have a table with a few objects, you have a drawer, and it's learned in this restricted area where everything is nicely visible, predictable, it doesn't have any interaction with the human. Also, the human is sometimes moving the object to show the robustness. So this is where we are, and it's still far from what the industry expects, but I believe that we are getting there. And I think that I can end here, and thank you.
Are there any questions for Carla? Yes, please.
Thank you for excellent and really understandable presentation. Question: how many years we will need to reach the level of your of quality of your programming to the level we have seen in the film Terminator?
Okay, now there is a problem. I don't remember the movie Terminator. I saw it very, very when I was a kid with my mother. So but I guess that it was like just Schwarzenegger strong and working for every command. Okay, I don't have an answer to this. It seems that it's moving, like now we have all the pieces. And that was, for me, this is like the step I saw it, like when I started the PhD, we didn't have the pieces. We didn't have the good speech recognition. We didn't have the good vision. And those are like basically the necessary pieces that you can start actually to build on top the understanding of the task and teaching and communicating. So we have the pieces, and now there is a huge focus of all the researchers to actually make this embodied reasoning and mapping. And I have no idea. I guess that in 5 years, we will have something which already is applied in industry in specific areas, but it will still not be robust, adaptable. It will not be able to learn by itself in new environments. So it will actually work in the industry and fulfill what SMEs need for their tasks, but for the real, like it's about when we will have the general AI finally working, it's the same question basically. I think this needs the thing. You need that the robot is actually understanding, and I don't know, it can be 10 years, it can be 50 years, it can be 100 years, but not more. 2060, okay, then I made a good guess.
So we have one more question here.
Thanks for the talk. If I understood that correctly, then you're essentially learning from positive examples and sort of positive instructions. I was wondering how harder is it, or would it be to embed in your framework also instructions such as don't do this or don't do it this way, or whether there should be some active participation on the side of the robot in case of, uncertainty. What is and what is not allowed. And in principle, imitation is one thing, and then sort of generally prohibiting something. And you can show it on an example, but that still doesn't really capture the class of all the behaviors that are prohibited. So how harder is it to deal with that?
Okay. Thank you for a question. Yes, we are learning so far mainly from positive examples, and it's already difficult to include even I made a mistake and now correct it, even like for language, for synchronization, and for everything. So that's from my side like first step that we actually can correct somehow. To your question about a negative example, I think it's a great direction. Actually, with Ivana Krujf-Gorbayova, we are writing a proposal exactly on this, because it seems to be the way how very often we are learning, like in parallel, and how it can be incorporated to my model or to our models. I don't know yet. We have like basically there will be some dialogue system next to it, and then I guess it will just have to be different model, and I don't know yet. But we can discuss it. And actually, one way, which is definitely the direction for us, is also the behavior trees and decision trees. So I like the talk because for the robot movements and actioning, it's great if you have this reasoning on top and you can decide and verify it. So I was very happy about the talk because I agree.
Okay, excellent. Thank you very much. Let's thank Carla again for the wonderful talk.
Let me introduce the next speaker, Christian Wolf, who is a principal scientist in Naval Lab Europe in Grenoble, while being on leave of a position of associate professor in INSA Lyon. In Naval, Christian, you are leading the team Spatial AI, with a special interest in embedded computer vision and in machine learning for robotics in general. So with Christian, we will see a lot of robot navigating in a partially known environment. You also have a lot of investment in research network in France, like GDR-ISIS or GDR-AI. Today, you are supposed to discuss how to learn representation to visually guide robot navigating in a 3D environment. So the floor is yours.
Thank you very much, Nicola, for this really nice introduction and also for the invitation to the organizers. I'm very happy to be here. So yes, as I will talk about navigation today, and as Nicola said, I'm part of Naval Labs, but actually I recently joined Naval Labs. I have been an academic for a couple of years at INSA Lyon, associate professor. So the company Naval I'm working for, you know it perhaps, is global, and they have lots of activities in internet search, online shopping, recommendation systems, NLP, etc. And we at Naval Labs, the research branch, are focused on ambient intelligence, so technology which is aware of you, yourself, and your surroundings. And in particular, one of the applications we're working on and proud of is navigation. So what you see here is a video. I forgot the subtitles because I just cut it together from various sources. So this is the new headquarters from Naval Labs in Seoul, in Korea. And what you see here is one of, or several of the roughly 100 robots which are already actually navigating there. So this is a production system. Naval employees can actually right now order coffee or send packets around. So you can, with a small cell phone, ask a request a robot. The robot comes to you, it opens a hatch, you can put something in, and the robot is actually fully autonomous and can deliver parcels, coffee, and whatever you want. So this is done with computer vision, machine learning. The building has been 3D scanned, for example, etc. So what I will talk today is about this kind of navigation ideas and the new research we'll do. So for the moment, the slides I will present today are mostly the work I did before joining Naver, so which I did with my old PhD group at INSA Lyon. We will work on learning navigation. And so how is navigation being dealt with in the past? Well, basically there are two schools which try to join themselves, classical robotics. And in classical robotics, navigation is heavily based on geometry, maps, localization. So SLAM, for example, the robot actually navigates, builds some kind of 2D or 3D map, and then there are planning algorithms on top of them. Now, all this research has been improved and augmented with machine learning, but still lacks some kind of robustness because, for example, because the situation is not exactly as we try to model it. On the other side of the spectrum, we have machine learning, where basically navigation is trained in large-scale simulation. So here, what you see here is our building in Inria France, where I work. Either seen from the physical robot or in simulation after we 3D scan the building. So we can train robots to navigate, to solve tasks here, and then the problem is how can we make them generalize? So there are also problems, of course, no solution is perfect, and here also we have lack of robustness because typically the simulated situation does not correspond to the real one, so this is the famous sim to real gap, and we need to overcome this. So let's step a little bit back for 1 second, and when we try to find out how can we solve this problem, let's find out what kind of reasoning skills robots actually need to learn. And I tried to come up with 4 of them. So probably the simplest thing which a robot needs to do is obstacle avoidance. So find out what piece on the floor is actually navigable or occupied or in motion, and if it is, stop, go around, etc. So this is related to quite local scene structure. Oh, that was too fast. And if we extend scene structure a little bit further, then navigation also needs to find a local minima, for example. We can't just always follow the Euclidean path to a target. This requires, for example, if I need to exit a room, well, find the exit, find the door. And as in the case here at our robot in Seoul here, well, these robots are actually capable of taking elevators. Well, we need to find the elevator if we need to change the floor. So this is still related to scene structure. A little bit more complex is discovering affordances. So what does this mean? That means the world around is, well, full of people, objects, and some of these objects can actually be interacted with. So for example, here we see that there are keys on the floor of this apartment. And if the robot actually sees them, well, if its current task is to find the keys, well, obviously it should pick them up and get them. But actually, it should not even wait for the task to be specified. If it sees the keys, it could actually anticipate, okay, in the past, I have been asked to find these keys. Perhaps I should just map them so I can find them quicker next time. And actually, we don't want to hard code that. We want actually the robot to discover automatically which actions, which objects are important. And if it's really smart, actually takes the keys and puts it where they should be, right at the, the thing right beside your door where all your keys are in. And last thing is, well, if we push this a little bit further, then robots should actually be capable of understanding important parts of the world we're living in. So I'll give you one example. So let's say that you want a pillow and you ask the robot to find your pillow. Well, I will not go into details why you should actually, it would be easy to go to the bedroom, but anyway, let's say the robot should find a pillow. So the robot navigates and it finds here, it sees a glimpse of a bedroom here. So you can't imagine that the robot thinks, I need a pillow, there is a bedroom, perhaps I should search there first. So obviously you could hard code that for the specific case of a pillow, but why wouldn't you want to have the robot, why don't you want to have the robot to have a model of the world, tap into some knowledge sources? So for example, tap into language models, and there are recent papers here, for example, in the monologue paper, or the LMNAV paper, which actually try to do that. So they actually use models like GPT-3 or these large language models to actually communicate knowledge to the robot. So this is the goal we have. And we need to do that in large-scale training. And today I will focus a little bit on the types of spatial memory we can put into robots, because robots need to reason, and when they reason, well, they have seen things in the past. They will not try to store everything they have seen, but they have they will probably learn some representation of the history of observations. And the simplest thing in pure machine learning we can think about is what is called, oh, sorry, I'm still trying to find out what these buttons are. So the simplest baseline we can think about in machine learning, if you want to give a process memory, is the recurrent baseline, where you basically put some LS. Okay, I'm sorry. These buttons seem to be correlated. So you put some recurrent memory, like an LSTM or CIIRC, into an agent. So the agent here takes a decision on an action to take. So for example, move to a certain direction. He has its old memory, updates its memory, and as an input it gets the current observation. So for example, an image from a sensor. The goal, for example, a goal embedding, what task should I actually solve, and eventually the previous action. So this is the simplest form of memory. We'll come back to it, but we can do better. So what I will talk today here is 4 forms of memory which are currently discussed in the field of AI for robotics, 2 of which are pretty classical. Metric maps and topological maps have been here for some time in robotics. And they have been what we can call neuralized, so they have been put into neural networks beyond just using these maps as input neural networks. So how does this work? Let's start with, for example, metric maps. So you can start again with this projective neural, with this recurrent baseline, which for the moment only has this vectorial flat representation. And you can give it additional memory. So this is work done by my student, Edward Beeching. And you can, for example, say that I'll take the egocentric observation here, calculate features from it, and then I do inverse projection to some latent map. Here, this inverse projection requires camera calibration, camera intrinsics, and depth. You need a depth tensor for that. And then you project actually pixels from here to the latent map, and this projection is still learned. So what actually is put on a specific point on the map is learned. Where it is put is not learned. This follows geometry. So this is one version how to mix geometry and learning. And we showed here in this work that this can be learned by reinforcement learning. And we can even augment this with some form of attention reader where the agent can basically say, I would like to find out what happens here, or I would like to find this in the object. So this combines actually 2 forms of memory, and this memory also can be seen as a bird's eye view tensor, right? It follows the agent, so as the agent moves, the memory follows it and moves with it, like classical metric maps in robotics. So we have also shown in recent work that this can be combined with self-supervised learning and learning from privileged information in simulation. And together with projective mapping, we obtained first rank in the multi-object navigation challenge last year. So this is work by my student Pierre Marza. Okay, now the field actually had some interesting development with respect to these maps, because these maps require 2 things. They require camera intrinsics, which are not complicated to get by, but also depth, right? But depth is either difficult in certain situations or noisy. So recent work, there are a couple of papers here, among which is the ICRA-best paper, this year's ICRA-best paper. It changes a little bit, so they still use camera intrinsics to find the correspondence between image columns in the egocentric image and polar rays in the bird's eye view. But the remaining ambiguity, which requires depth to solve the position on the column versus the position on the polar ray, is then solved through large-scale machine learning from data. So basically, you find out how objects look like and where they could be on the polar ray. So next are topological maps, which are also quite used in robotics classically, and they can also be put into neural networks. So topological maps are basically graphs. This is how you determine in the morning how to go to the bakery, right? You don't reconstruct a 3D model from the environment. Probably you see first I need to go to the door, from the door I need to go to, etc., etc. So we have worked on that also, where we try to find out how we can make the robot cope with topological maps it produces itself, which are inherently uncertain. So if the robot produces points in space and then links them through connectivity. It thinks, okay, this point here should be connected to this point. It might be wrong, right? So this is all uncertain. And what we did here is we created with various algorithms 75 million of these graphs and then learned how to solve these graphs, including this uncertainty. So we train on multiple instances, and then with the knowledge gained on these instances, how are these uncertainties actually probabilistically distributed, we can better solve a single instance. I'll give you one example here. In simulation, so the purple points here are actually graph edges, and the robot here plans first on a higher level, so this is a hierarchical process. The robot learns first which graph vertices to plan to, and between two graph vertices, actually we use a local policy trained on with reinforcement learning, in which takes the visual input as guidance. So this works actually pretty well. Next thing is temporal attention. So while the first two maps here are classically used in robotics for a long time, the next two actually are really machine learning contributions, and in particular temporal attention, which obviously, as you probably know, dominates machine learning in practically every field we can imagine right now. And this also has been used for navigation. I will not go into details. So this is my only slide. There is lots of work, recent work. Cordelia also has work on that, the episodic transformer. So how does this work? Basically, these models break the Markovian assumption in decision taking, and instead of taking the decision based on some memory which we maintain, they actually make it possible to attend over either the full history of observations or at least a very, very long horizon of that. And that can improve performance a lot. I will not go more into details here because I will actually spend the remainder of this talk to work we have proposed recently, which are implicit representations for navigation. So what are implicit representations? You heard about nerves probably. I actually found it quite difficult to define what an implicit representation is, and I found two different definitions. First, through the implicit function theorem, which is used when you have some function of interest, phi here, and you don't have an easy means to explicitly specify it, but you can do it by proposing a second function f, and the level set of this function here corresponds to the function which really interests you. That's one way of seeing implicit representations. The second one is an implicit representation. It's basically a representation of some geometric object, a shape or a scene or something like that. And instead of defining the shape explicitly through some discretized representation like meshes or voxels, you can actually learn parameterized neural networks which map coordinates through some quantities of interest like density, occupancy, sign distance. There's even an overlap here because if your function f here is a sign distance field, then this f here corresponds to this, and the level set of the sign distance field would then be the surface of your scene. So how are these things used in robotics? Well, in various ways. For example, here we have representations. They're always representations of the scene. For example, here we have an implicit representation of the sign distance to a target. This means that navigation is basically gradient descent. You can do gradient descent on the representation. Here, model predictive control is augmented with an implicit representation which lets you avoid occupancy. But in this kind of work, I don't know how the other speakers did it, but I'm really troubled here. So I honestly push the right buttons, but they're correlated. My fingers are too big, I guess. Yes. Okay, something is happening here. Yes. So these two line of works actually require that the representation has been created before the episode. They are not dynamically created, so you need to first reconstruct the scene and then you navigate. Then there is recent work, for example, this work here by Andrew Davidson's group, where the representations here, nerves, are actually generated dynamically. So as the robot navigates through the scene, it generates the representation. But on the other hand, the representation is not used for the navigation process itself. So there is no downstream task on navigation which uses the representation. So in our group, actually, we would like to tackle that. And what we proposed is exactly this. So we proposed two different types of implicit representations. So this is work of my student Pierre in collaboration with colleagues from INSA Lyon. And so these are 2D implicit representations, and they are dynamically created. So at each robot step, at each step of the agent, we need to update a map, and the map is a neural network. So we need to do backpropagation and learning even after training the robot. After training is deployed, learning is done at each step. And this is a lifelong learning problem, since if you do that, then what you learn at the beginning of the scene must not be forgotten at the end of the scene, which can be done if you just naively train your neural network. So we have two different representations here. The first one is a semantic finder, which actually directly maps semantic embeddings to positions, and this allows to store where key objects are, for example, where are things I might search, but which is not so helpful in finding out where occupants is and how can I actually avoid obstacles. So we have a second one. And the second representation is a coordinate network, like a nerve. So it maps coordinates directly to information of the scene. In this case, 3 classes: unexplored, navigable, or occupied. And so both of these are input to an agent, which updates them and uses them on the fly. So the problem with the second one here is that we probably need some global reader on that, because as we put coordinates into the network, planning would require that I iteratively actually query it, say, can I go here, can I go here, can I go here? And if I just want to solve something like an A-star algorithm, then it would result in a large amount of queries here, which is obviously not tractable. So what we proposed here is a global read which directly maps from the function space, because this is a function here, maps from function space directly to some embedding space from which I actually can navigate. So that's exactly what we did. We have this global reader, and the function space is represented by the neural network weights itself. So we train a second neural network, which is trained once for all, not dynamically. We train a second network, a global reader, which maps from the neural networks of the implicit representation directly to a usable embedding. I will not go into details. This raises a couple of questions. For example, a desired property we would like to have is invariance. If I have 2 different representations which are the same function, then we would like to have the same embedding. The problem is this representation is implicit. It's an MLP. And if I take one MLP, I'll take 2 hidden units of this MLP and I permutate them. I maintain the same function, but it's different weight matrices, right? So we don't have this invariance property which we require. And we couldn't solve this exactly, but we go into this direction using a transformer-based solution. I will not have the time to talk about that. So I'll finish up by just showing how this actually works. This is the same recurrent baseline I have showed before. So I still have this recurrent memory here. We have the same inputs. And what we just do is we add these 2 implicit representations here. So the first one is connected to the query, the target we need. And the second one basically means the global reader here just is input to, the output of the global reader is input to the agent. Now, of course, we need to fill these guys. So what we do is we use a replay buffer during training. Training means during each agent update. And this replay buffer is filled from observations. So we have the visual observation here. We do some pre-processing here. This fills a replay buffer, and the replay buffer, from the replay buffer, we sample batches and update at each agent step. We update the implicit representations. This works quite well. I'll finish with results. So this is work which is currently under review. We'll get the review, hopefully the answer tomorrow. And we obtain new state-of-art results on multi-object navigation with this technique. I'll wrap up here. So as a conclusion, we are interested in creating robots which are situation aware, which are capable of high-level reasoning, and we put a strong focus on sim-to-real performance, so performance in real environments. And to that end, we combine machine learning, computer vision, geometry. This requires large-scale training, finding the proper inductive biases, so how can we organize memory in robots in the most efficient way. Thank you very much. I'm happy to take questions.
Thank you for the nice talk. I think we have time for one question. We have some questions in the room.
I have a clarification question. So your reader needs to be reading a neural network representation so that it better generalizes. You get into the situation where you might need the key, and then the F. I mean, what you had as the F that is read by the reader. That needs, what is exactly the advantage of the F being the implicit representation that is the neural network and not, say, a classical map where, your keys are and something that is more transparent? Does that more transparent, more traditional thing generalize worse, or why do you need the implicit representation there when you still have the reader afterwards?
Okay, that's an excellent question, and it's true that I didn't actually talk about it, and I should have. So. There are a couple of advantages of the implicit representation. First of all, it has a fixed budget, and it can, if you have a tensor, a metric tensor, then basically current metric tensor is limited to 32, 48, 50 values, at least in the neural ones, right? If you run ROS on your robot, you can have maps which are very, very large. But if you use them as inductive Bayesian neural network, you can't do that for lots of reasons. Just the amount of memory which needs to do pass through is just not possible. So these maps are very small, and which means basically when the robot moves out of its history window, it has forgotten what it had seen before. So here you're in a fixed budget, and basically the network itself adapts to its amount of information it has seen. The second thing is, neural networks are pretty good at interpolation, and we exploit this here. So if you haven't seen something in a metric map, then there are holes, right? And if there are holes in there, then the planner will just fail. Whereas here, through the fact that it's a neural network and it interpolates, hopefully, and that's what we a little bit checked in the paper, you can use this through interpolate through, right? So.
Thank you. Thank you for the answer. So the next speaker and the final speaker for this session would be Thomas Svoboda. I learned about the work of Thomas from the recent success of your team in the CIIRC challenge from the DARPA in collaboration with the University of Laval in Canada. But actually your work ranges much further in vision for robotics, from omnidirectional camera to LiDARs, from object recognition to terrain detection for advanced navigation. So today you are mostly focusing on the CIIRC challenge from DARPA. I'm pleased to hear about that.
Okay, thank you. Surprised that you remind the omnidirectional vision, because you can't remember. Definitely you can't. That's an old story. Okay, so this will be a kind of a system talk about what needs to be done when you want to send robots into unknown environments. So of course there's a lot of collaborators in the team I was honored to lead in the past 4 years actually. So the motivation what we did was based on the DARPA Sub-T challenge specification. So it was a 3 years long competition, say challenge/competition, where the robots were asked to go into unknown environment and find and locate as many objects as possible in the given time. Why we entered this actually? So when we were discussing whether to join this competition or challenge or not, we actually quite quickly decided to go for, because previously we did quite interesting work with European rescuers. So this just snapshots in the Amatrice 2016, where our robots were doing some jobs for the Italian firefighters. But in a way, the rescuers are, in a sense, like medical doctors. They like tools, but they want to control them. And they are kind of unhappy when the machines do not react as they want, and if they do not react quickly enough. And we definitely want to took the autonomy challenge to really, to send the robots alone in the environment. So just quick reminder, I suppose that most of you know about DARPA challenges. Long story. For me, the beginning with DARPA challenges was in the 2004 and 5, because I'm very interested in cars, in car making industry, and how the cars are developing. So it was the beginning for me. I was reading a lot about, and yeah. So I was quite happy to join such kind of thing. I never even thought in the 2 decades ago that I would be able to join. So this is just a few snapshots of our robots that joined the competition. So at the end, we really had everything, flying, wheeled, tracked, legged, 4-legged, 6-legged robots of different sizes. Because the thing was, we didn't really know exactly what to expect. The environments were really unknown. Okay, so recently when we got the additional funding from DARPA, we purchased the spots. So just short reminder, what you can buy is the yellow thing. What's up on that, it's our making, both hardware and the software. This is what you need to send the spot into unknown environment. Even though this spot received a lot of attraction, actually I personally liked more this guy, the articulated tracked robots. But again, on top of it, you need some sensors and so on, computational power. And of course, the flying guys, have to do the computation and sensing as well to keep airborne long enough to find objects. We also do have quite a stranger robots, even though we didn't use this one because of the kind of environment that we were faced in the final. I'd like to show, but because I suppose that not many of you seen these 6-legged robots. It looks kind of funny. The good thing is it's really robust. You can send it to the mud and it survives simply. And it can submerge, of course, unless you put some additional sensors on top of it. So we wanted to be really kind of flexible, so the sensing and the computational part needed for the complete autonomy could be put into nearly any robot of adequate size. And of course, we needed some kind of communication. I will come back during my talk. So what was the rules of the game, actually? The rules were quite simple. And we were talking to the DARPA guys, how did they find it? And it was actually quite realistic to hear their reasoning, because they wanted really to know what's the state of the art in the autonomy of the robot, in the true autonomy. So they are thinking about various metrics like the path traveled, the space mapped, and so on. But at the end, they narrow it down and they say, okay, what matters is whether the robots are able to find the objects or victim, you name it. So this was really, and the rules were made in a way to mimic the real deployment as possible. So they took the teams out of the garage, brought them into the front of the entrance in the environment, and then the team had then 30 minutes, half an hour to prepare all the equipment, to solve the cable salads and so on, to calibrate the robots and so on. Then the clock starts ticking, and the teams had 60 minutes, or the robots, to find as many objects as possible. And the truth is that the system didn't really need to be fully autonomous, but only one person was allowed kind of to communicate with the robots, provided there was any connection. So pictorially, in garage, bring the robots, bring out of the van and so on, solving cable salads, calibrating the robots, because as I mentioned, the goal was not only find but also to locate. So at the entrance, you can see the entrance door. There are some calibration marks. So all the robots had to be calibrated to the one unique coordinated frame. And then the robots went in. There was no limit for number of robots, kind of the robots, and so on. And report, it's also important to report the objects and the position. So of course, the robots might go in very deep, losing the connection, but in order to get some points, the robots had to go back close enough to report the found objects. Once again, only one person was able to communicate, and even though there was no help allowed, so even the other guy standing around couldn't interfere with the guy looking at the screen. So what is the building bricks? I suppose the robotics guys know already. So you need the 3D mapping, obviously. You need some algorithms for exploration. Exploration meaning that the robots sensing environment it never seen before. So the robot has to decide where to go next. That's the exploration in my understanding. The object detection. And I mean, to get the system working, you need some high-level control of the overall system, and to get the points, you need to get out the information, so there's some communication needed. So the 3D mapping, actually, the environment was unknown, but very well suited for the 3D mapping. In fact, for the LiDAR-based 3D mapping. So with the rise of the 3D LiDARs, sort of all the teams at the end succeeded. So just visually, so this is the visualization of the mapping of the final round. And of course, the maps, I don't know how well it is visible, but of course, there is some work needed. You need to offload the maps to the drive because they get too big to keep it in memory. You need to recover from failure and so on, you can imagine. But interestingly, perhaps, is that we didn't use at the end any loop closure. So it was really incremental as the robot were going in. They were incrementally building the maps. Yet the accuracy was good enough to report the objects with the given tolerance. So to navigate the robot through the environment, you need obviously the denser maps. So the localization and the localization before was quite sparse maps. Because of the memory, you can create denser maps in the neighborhood, and you can do the reasoning about whether the robot can go there or not. Of course, the traversability capabilities of the individual robots are different. So you can well, we did some say training of the robots to find out what the actual traversability of the robots are. Where to go? I'd rather show this. There could be various strategies how to do the exploration. So for us, essentially, we did the detection based on the vision. So we wanted to increase the visual coverage of the environment as possible, and this was the driving metrics how to choose among various frontiers. So frontier is you can think about the point at the edge of the known world, so to say. And of course, as multiple robots were involved, it doesn't make much sense to duplicate the effort. So once coming at the crossing, the robots decided to go to the explored environment. Yeah, well, actually, for the detection, as I said, we used mostly vision. There were kind of, at the end, 10 objects of various sizes, spanning from cell phone to a mannequin representing a human victim. There was also gas detection that was made on a special hardware. But simply speaking, we did the shopping in the computer vision world and applied the latest state-of-the-art method adequate for us. So at the end we used the YOLO, I think version 3. So this is just a glimpse of this is actually for the C. Does it run? Okay, somehow. Okay, it runs better on my computer. Just for the CTU guys, here is maybe interesting that these are the images from the CTU owned testing mine here near in Prague. It belongs, I think, to the Faculty of Civil Engineering. So we were allowed to go there and did some testing there. And of course, because the position was wanted, so we combined the vision, LiDAR, did some reasoning in space, and of course, we had to do some reasoning among multiple detections, because not only one robot could see the object from multiple positions, but also multiple robots could see the single object. And actually, the duplicate reporting were penalized by subtracting points. So in case you report one object twice, you lose the point and not getting 1 point more. So we had to do some kind of reasoning to avoid this. Communication. We use a different kind to achieve as much coverage as possible from wire at the staging area, say Wi-Fi in close neighborhood, then industrial or military grade solution Mobilicom, and our own breadcrumbs. This is perhaps the most interesting part. I'll come to in a second. Okay, the idea is quite simple. Either you could use powerful hardware to go as far as possible, but actually in a cave, the powerful hardware doesn't help much. So you could go the other way around, and you could use a small, cheap, disposable hardware and many such pieces. And you can go and you can drop the parts whenever you think it's needed for keeping the connection going. In practice, it may look like that. This is a snapshot from the Prague underground, and the spot is losing is dropping the communication modes. One of the interesting tasks we did some research is how to find out the right spaces, because the connection strength may depend on many things, on material, on the terrain, the robot traverse, and so on. So we really wanted to learn or create a model that would be able to predict the right positions based on the map created so far. So this is just a glimpse of the operator console, because at the end, when the objects were reported, it was quite reasonable to think, okay, it may be better to get a little bit more false positives, because at the end, the human operator was able kind of to cancel the obvious false positives. Actually, there was a limit how many times you could report the object. So in most of the runs, there were 20 objects placed in the world, and the teams had 40, so twice as many trials to report, and not more. Okay, How it looked, so this is just a DARPA material. So this is from the urban circuit. And the urban underground was here represented by the underground of the nearly finished nuclear power plant, but never put into operation in Washington State. Very nice environment for roboticists. I mean, a lot of challenges. You can think about 3D environment, a lot of obstacles, and so on. So this is how our robot team did. Okay. So here you can see the tracked robots. These are the videos we were given after the competition, because the DARPA organizers put essentially the surveillance everywhere to get an overview. Here is what you can think about the robot is doing mapping, assessing the traversability and controlling the flippers in a way that safely descends the staircase several floors down. There will be one detection, kind of a simple one, detecting a red backpack, which is quite easy. The other objects were more complicated. Okay, the flying guys, of course, they had to do the same. So the mapping, finding objects, reporting, staying airborne, and so on. So actually this environment was sort of good enough for flying. There was enough free space. The final event was not so favorite to the flying. It was much narrower, so not that much flying in there. But in this power plant, it was quite useful to use the flying robots. Just maybe for you interesting how the DARPA did the combining all the challenges. So these are how it looked, the environment where the robots were supposed to move. And in fact, the DARPA built a several hundred meters long maze of corridors of different kind within a Limrock cave in Kentucky. So really huge effort DARPA put into organizing. I think that all robotists would have loved to have such kind of playground close to the labs. So this is the map, how it looked. But of course, we didn't see the map before the competition. So just snapshots, the robots, okay, going there. Okay, so this is how it looked from the, okay, so I'm obviously running out of time. So we did quite well, and this is just a snapshot. So thank you for your attention.
You were actually faster than the load. You could have taken one more minute.
No, okay, so sorry.
Very nice work. I saw an earlier version of this talk where you did a sort of praised really the wheeled robots. It's very fast. Now it seems a lot of work was done by the spot. Can you just say in the end what was the platform which you found the most successful in this?
So overall, throughout the years, I think that the tracked robots did most of the job. But of course, it was partly because the spots was not available, at least for us, till the final. At the end, the good thing on the spots was that they were reliable from the hardware point of view, except some problems with the rear camera, but the Boston Dynamics guys repaired it quite quickly. So the hardware reliability. From the kind of traversability and stable locomotion, I think that for this kind of environment, perhaps the tracked robot's still better, because there are a lot of smaller and bigger rocks, on the floor, which is not very favorite for the spot. So for this thing, I think that the tracked robot's better. But the spots did equally good job for us during the final event.
Do we have one last question for the session? If not, maybe we can close because we are already a little bit late with respect to the schedule. You really want a last one?
I'm very impressed by this work, but so how much autonomy? Can you just comment, like how much was teleoperated, how much was autonomy? Yeah.
So at the end, there was actually for us, it was more autonomy than actually needed because the environment was relatively small. So some teams actually reported they were able to keep the connection throughout the whole course. But we had some problem with the connection and the distributed databases. So most of the robots, especially the spots who went in some of the courses, were on their own. But it was still the kind of assisted autonomy. So throughout the 60 minutes, so the operator definitely had the chance to communicate with the robots, like sending him to the right and commanding go back in that way. So it was not fully autonomous. We did full autonomy in this simulated environment. There was no communication possible. But for that, it was assisted autonomy.
Okay, let's close the session. Thank you for your attention. Thank you to the speakers.
Stairs, come for the lunches upstairs, and we'll be starting in the last session after the lunch here. Don't forget, if you are interested in the tour for the autonomous driving facility at Valeo tomorrow morning, register, please. Register for it. It's an impressive facility with a test track. Register at the registration. Thank you.
Have to plug it in there, right?
Yeah, I did it.
It is usually possible. So I hope that
the others are like animated clips, right? Yeah. So they play and then the last one we
Okay, welcome back. I see that Joseph Sivic is arriving. So we are going to resume with the afternoon session on computer vision and trustworthy systems. And the first talk will be given by Cornelia Schmidt. She's one of the most prominent researchers in our field. She's a distinguished scientist at Inria in Paris. At the same time, she's with Google Research. What can I say more? She's with the German National Science Academy, and just one thing I can also mention is that I think she's the only person, at least I know, who has received 3 times the test of time paper 1 at CVPR, and she's going to tell us about large-scale learning from multimodal videos. Thank you.
That's fine. Thank you, Patrick, for the introduction. So today I'm going to talk about large-scale learning from multimodal videos. So first of all, what are the rationale for using multimodal video representations? If we want to precisely understand the video content, we need to have access to all modalities simultaneously. For example, if we look at the video here, we can see that the man is serving food, but only if we hear the audio, is this Indian, do we know that he's serving Indian food. Another reason for using multimodal videos is that videos come with speech. Speech can be transcribed with ASR, and we can use this data for large-scale cross-modal vision supervision with no manual annotation. So here, this can be, we'll see this later, but this can be used either for pre-training, we have seen some of this yesterday, or what people are looking into more and more is to use this data for zero-shot learning and basically don't have to use any or very few annotated examples for training. Okay, so here in this talk, I'll first show 2 of our recent approaches for large-scale automatic training data collection, then show the importance of the loss function in the models in the context of audiovisual speech recognition, and then terminate with a small example of our work on multimodal transformers for navigation tasks, similar to what we have seen in the previous session. So for this task of vision question answering, if we have, for example, the how to 100 million data set, we only have videos and text, but we don't have question answers. And so here, this first work was doing cross-modal supervision for obtaining videos with corresponding questions and answers. And here, the idea is to use the trick that we have these clips from how to 1 million and the speech transcribed with ASR. And this allows us first to get precise clips with aligned sentences. And then the other information which we use is the, okay, somehow it's also not working, is what we can see here on the right, on the left, is that there's a large corpus of text where people have actually annotated for given paragraphs the corresponding questions and answers. So this has been done for text, and now the idea is actually to use this cross-modal information to leverage these 2 informations jointly and use this to auto-annotate these existing videos. And so what we do here, we have these clips with transcribed ASR. We have now, okay, here, our model, our annotated model, for which we can then train transformers or models that give us back for a paragraph the corresponding answer and the corresponding question. So what we have now, we can take as input a sentence, we obtain the answer and the question. First the answer, so the model looks for the answer in the text, the paragraph, and then the corresponding question. And so we can apply this here to our sentences. We have the sentence transcribed from the video with ASR. We obtain the corresponding answer and the corresponding question. And so what we have now, we have here, we can see here, we have the video clip. The ASR is add some of your favorite sprinkles, give it a mix. And then, given this sentence, we can use the transformer model, which we have pre-trained on this annotated text corpus to generate the question, what can you add to the mix, and generate the answer, sprinkles. And so here we can then auto-annotate this large-scale corpus of 69 million video question answer pairs. If you look at them in more detail, we obtain the average clip is 12 seconds long and annotated with 1.2 question answer pairs. And we have a total of this 69 million video question answer triplets. And if we look at the quality is relatively high. We have 30% where actually the question is correct and matches the visual content. 39 are correct but don't match the visual content, and 31% are incorrect. And so this is enough to pre-train and train a large-scale video question answering architecture based on contrastive learning. So the contrastive learning takes as input positive and negative answers. It can deal with this large-scale corpus. Here are 16 million different answers, and what we have here is input. First, we take as input the video and the question. This is fed as one input to the contrastive learning. The second input is the answer, and then we learn actually what is matching between video question and answers. And this allows us afterwards for video question pair to predict the correct answer. So similar what is done for the clip model. And if you now look at the zero-shot results, so zero-shot means that there is no annotated at all, any annotated pairs. So we just have this completely automatic large-scale corpus which has been scraped from the text, from the web, and the results are reported on state-of-the-art data sets for which we have obviously for the test data only the annotations. And so if we look at what we get if we use random data for pre-training, we can see that basically the results are completely random. And then if we use our data set, we can see, so IVQA is one of the video question answer data sets. We can see top one, 12% of the top one answers are correct. And then if you look at the 10 best replies, we can see 43 of them are correct. So it's not perfect, but it's much better than if we had only no pre-training, right? And then similar for another data set, MSVD, we can also see that the performance is much better than random. And here just an example of the zero-shot results. So remember, here we have no manual annotation of any training data. And so here the question is, what is the largest object at the right of the man? Our answer is wheelbarrow. And then what's also interesting is to look at what we would obtain if it was text only. It would be statue. And this is basically because in many images there are statues next to the person, right? And then the other thing which we can do with this large-scale training data, so what we have seen yesterday, we can obviously also use it for pre-training, right? So there basically the idea is, here the first thing we have shown, that's actually what I'm more interested in, is the zero-shot learning, that we can really learn without any annotations, but then we can also use this large-scale data for pre-training, and we can see here in the second row the results for training just on the training data without pre-training. We can see then if we use this large-scale data set for pre-training, we improve significantly the performance. So this is similar to what we have seen yesterday for language, and here we can also see that this translates nicely to video and language combined. And so basically here we have seen that we can use this weak supervision to exploit the large amount of data available online. You can see that we can use intelligently the correlation between different modalities, to use different types of annotations, to combine them, use them jointly. We've seen that there's excellent performance for zero-shot results for zero-shot performance. And then one open question, which is very interesting, is to how to further improve this zero-shot performance. So we've seen that it's very good, but basically it's not matching the fully supervised results yet. And then obviously there are a lot of intermediate works where people use only few-shot to clean up the data, but I think in the long term it's really interesting to see how you can match better, even better, the language to the video to clean out incorrect examples. And then another thing which I'm going to address in the following is how to extend this to additional domains. So here we've just seen that it was working for the instructional videos, which is how to 1 million, but then there's obviously many more domains, and we're interested not only to cover one domain, but to extend it to more varied domains. And this is a recent work of how to learn audiovisual modalities from image captions. And here, again, the idea is we rely on existing annotations to extend them to video and audio. So here what we do is we transfer image captions to video and audio. And this allows us actually to create, in a weakly supervised way, new data sets of annotated videos, so videos with captions, and also audio sounds with captions. And so what we do here is we start with the seed image captioning data sets. So people have actually annotated this large-scale, relatively clean image captioning data sets. They're not completely clean, like, for example, conceptual captions. So you have these data sets where you have images and corresponding captions. And the idea here is to use these images as initial seeds to search for corresponding videos online. And so the idea is to find frames in videos with high similarity scores, which match the seeds images, and then we can actually crop the corresponding clips from the videos and transfer the image caption to these videos. And so this allows us, for each image, we can not only crop one video, but we can crop many of them, right? So we can really expand the data set, and it can actually go to a very large data set given this procedure, right? And then basically to do the matching between the image and the video, we have some similarity metric and the matching score, but that's actually not very important, the type of similarity matching, and the matching score has to just guarantee that there's some matching with the images. And then interestingly, what we can see here, basically if we compare what I said before, the domains in how to 1 million and the domains in our new video CC data set, we can actually see that the domains are much more varied. So if you look at how to 1 million, a lot of things deal with food and hobbies, while in this new data set, there's a much larger distribution of the different classes. And the size here is 10 million, can be further scaled up. It's multimodal, it's truly multimodal. We have both video, audio captions, so it's really, we can really extend it to this truly multimodal data. If you look at other data sets, they're often lacking audio, they're often lacking speech, they're small because they're manually annotated, or there's how to 1 million, then here what we see is that it's much more balanced. And so here, if you look at a few examples, we can see on the left the seed image. So a person throws a pitch during a game against the university. You can see the seed image, and we can see the correspondingly mined videos, which match the captions very well. And then similarly, the next one is the music rap artists perform on stage during the day, during the festival. Again, we can see that the corresponding videos match the caption very well. And so then, as I said before, again, we can use this for zero-shot results. Here it's for video retrieval. So we use a standard method based on contrastive learning to extract video features based on a recent transformer-based architecture, which is VID. That doesn't really matter. And an architecture to extract features from the text. Here it's clip-based, similar to clip-based BERT model. And then we can learn with contrastive learning based on this data set, the matching between the text and the video features. So we have this large-scale data set, completely automatic. And here what we can see is comparing the different versions. Obviously, if you have no pre-training, then the results don't make any sense. If we have pre-training on how to 1 million, so we do this contrastive pre-training on how to 1 million, we can actually see that the results are significantly lower than if we use our new data set. So they go up from 8.6 to 18.9. That's a really significant increase in performance, and this can be explained by the fact that the data set is much more varied. And And then basically what you see here, we call it 1, we recall it 5, recall it 10. You can see, obviously, if you look at the 10 best examples, the performance goes up. And if you look here, basically for recall at 10, we're already at 50%, which is very high. And then the last line, what it shows in the table on the top, if you add, in addition, the audio features, so you can take as input to your training procedure either the video frames, but you can also represent the audio as by using spectrograms similarly to features. So you can also extract features from the audio and then combine them by some type of fusion, either early or late fusion. You can see that this gives you an additional 2% in performance. And similarly, we can also show, I don't have the results here, that you can use the same pipeline to describe audio signals only. Right? So you can also just do retrieval of audio sounds. And then the table on the bottom, you can see actually the comparison of our work to the state of the art, so it outperforms all of the competing state-of-the-art methods. And then something which is actually also interesting, we have extended it to zero-shot video captioning. So this is actually the first time people have performed zero-shot video captioning. So again, we just take this video CC data set, we train a captioning model. The captioning model which we use here is a standard encoder-decoder. So the encoder encodes the video features with a Vivid-based model. The decoder is a classical T5 decoder. And we can see here that, again, we get good results for zero-shot video captioning. So we just see this automatically collected data set and use this for zero-shot captioning. We can see that the results with our data set improve significantly over how to 1 million. Here the different scores are scores which are used traditionally to evaluate video captioning. So blue score, CIIRC, Meteor, which measure how similar the predictions are to the ground truth. And so if you look maybe more meaningfully, if you look at the result examples on the bottom, you can see on the top the ground truth. A man is discussing the parts in an engine compartment in a vehicle. Then if we use pre-training on how to 1 million, so I'm going to go ahead and remove this. Okay, not very meaningful. And then we do CC the engine bay of an automotive model. So you can actually see what is predicted here is maybe even better than the ground truth, and that kind of also shows the problem, obviously, of evaluating these video captioning models because there's no one specific ground truth. And then the second example, clouds are moving in the sky. And then the one which is pre-trained on how to 1 million is not so meaningful. And the last one, clouds moving in the blue sky, is actually, again, better than the ground truth. So you can really see that we get these very good results for zero-shot captioning. It also shows some of the problems with video captioning because it's really difficult to evaluate. But it's something which is for real-world applications obviously very important because it really means that you can describe the content of the video and use it afterwards for search. So we have seen with this new data set, we get excellent results for zero-shot audiovisual video retrieval and zero-shot video captioning. We have seen that it's really important which data you use for training and pre-training, in particular if you want to do zero-shot retrieval. And then future issues is how to further clean the data set and extend it and refine the temporal alignment. There's still work to be done to see how to make the zero-shot data even better. And then let's move to the second part, is what is important when we train these models. So far I've been only talking about the data. For me, the data is one of the most important things. Basically, as we saw yesterday for language, it's really important what data is used for training. It impacts the performance. There's obviously all the issues which we have seen also yesterday about biases and so forth. But then, of course, it's also important how we set up the loss and the model, right? So basically, that's the second part. And I illustrate this with a recent example for audiovisual automatic speech recognition. So again, we've seen this yesterday. Speech recognition is not solved. 4 minutes, okay. Speech recognition is not solved, and so one thing, if we have not clean data, but noisy data, one idea here is to use, in addition, the visual content to inform the speech about what's important there. And so here on the left, we see our model. So here basically takes as input the video features, the frames from the video, the spectrograms from the audio. Here, the model which we have developed is like the bottleneck, the multimodal bottleneck transformer, where the tokens don't interact directly, but via the bottleneck tokens. So we've shown that this works better than early or late fusion. And then a state-of-the-art decoder, which takes this as an input. So this is the model. And what's important, if we train the model, is during training, we have to be very careful how we set up the training so that the model takes into account the visual information. And to do this, we have to mask our tokens and put noise on the audio data, right? If you just use the clean audio data, the task is too simple and it doesn't take into account the visual information. So we really have to make sure that the model pays attention to the visual stream. And so here, if we look at the results, so we have two evaluation settings, one cleaned and one noisy. We can see the top row is with no pre-training, so just learning the model from scratch on this small how-to training set. You're testing it on the how-to test set. The error rate is the word error rate. And what we can see here are two things. The audio, the visual information helps in all cases. And then secondly, the pre-training is very important, right? And then thirdly, basically masking out the words further improves the impact of the vision. And so I don't have much time. We can show that our approach outperforms the state of the art. We have collected a small data set where actually the vision is very important to decode the audio. And there we can see that the gain is more significant. And then here maybe just to show what are typical cases where we get an improvement. So this dessert definitely deserves a happy dance. This deserves and dessert. So basically by seeing the dessert, the model, our audio-visual model, interprets the object correctly, right? And so these are all cases when there's like either accents, I don't have the sound here, it didn't play, but either accents or, for example, the motor saw, you have a lot of background noise, and in this case, there's still like, as the person yesterday said, the speech is still not perfect, right? In these cases, the speech is still not perfect, and here, then the video can help. Okay, and then, well, we have seen that actually vision improves. It's important how to set up the pre-training and training losses. And what's interesting is to see how we could use the visual cues to further improve the performance. So here we have a gain, but it would be nice to even push the gain further, investigate this even more. And then the last part is actually to show that these models, this is what we have seen in the previous session, can be also used for navigation tasks. So we've seen, now I have one more minute. We've seen, okay, I can have a bit more, like people also talked a bit more. We have seen that basically before the transformer architectures could be used for pre-training language and vision models, but here the idea is that we also want to use it for navigation, right? And so here the idea was to design a fully based transformer model for predicting the actions. And so the idea is we take as input the text, so the instructions go straight behind the couch, the history, so what has been seen previously, the current observation, and then we predict the action, right? And so it's actually a very similar model, which is then used to predict the action. And the trick here is that we have the history of what has been observed before with the corresponding actions, and this allows us to remember what has been seen before. Okay, so here, this is our hierarchical model. I skipped this. It's also, again, important to have different losses for training and pre-training as before. So it's actually the message is hold. Here we can show that our approach outperforms the state of the art. Has been winning the Reverie and Sun challenges at ECCV 2021. And maybe, so what's interesting is the same things, basically, pre-training is important and the losses which are used are important. And then two extensions of what is missing here is generalization to unseen environment, right? If you have this transformer, it memorizes what we have seen so far, but if you go to a new house, it hasn't seen the new house before, so it's really not very well, cannot generalize very well. And so here, what we have been adding is adding how to build a map on the fly and add this map, so construct, while we're navigating around the environment, construct a map, and this helps us actually to see what's new. And I think this is kind of interesting, is to see how to combine these architectures which memorize with something where they learn something new, for example, here, the map. And then the last thing is how to apply it to real robots, and this is just take one last video. So basically this approach, HiveFormer, achieves state-of-the-art on LRL bench in single and multitask settings, but it also achieves excellent results on a real robot. So here we have a human instruction. So somebody says, press the red button, then press the black button, and press the white button, and the robot actually executes it well without having seen this exact sequence before, right? So this exact color sequence hasn't been seen before. So this is like a first attempt to port this vision language navigation to a real robot, and it kind of works here, so we're very happy. What's actually also interesting, we only fine-tune on a very small number of robot demonstrations, so 10 demonstrations per variation. And what's really important and what brings a lot of gain is this pre-training on the error bench. So the error bench is quite different from the real robot environment, but it still brings a significant gain. So again, basically the message holds, pre-training helps, and these architectures are really able also to be used for navigation. Okay, thank you.
Let's take one question in the room. I have one then. So it's impressive to see how much one can get out of multimodality without annotation. But yet there is noise, there is misalignment. Sometimes one modality sees something which doesn't exist in the other one, etc. Can you comment on the sort of the uncertainty or the noise it can also introduce and how to accommodate it?
I think basically what I've shown this evaluation. So if you have roughly 50% of the noise, then the model can handle it, right? It's kind of something which we have observed several times. If the noise is not the majority, the model can handle it, right? And so basically, if it's uncorrelated noise, I have the feeling that it can handle it quite well. And I think the main problem of the performance is more the gap between the missing examples and the examples which are there, right? So visual question answering, if you haven't seen this precise domain, it doesn't work, right? So it's not so much the noise, I think, which hampers you, because the noise is uncorrelated, right? And if the noise is uncorrelated, it doesn't make the performance drop too much. But what's really important is that the missing information, right? I think that's for me. Okay.
So, and the next talk in this session, we will have Jakub Mareček. We are very happy to have him here. So Jakub did his PhD at the University of Nottingham, then spent time in several startups and was a researcher at IBM Research in Ireland, also spending some time at University of California at Los Angeles. Currently, he's a faculty at the Czech Technical University, and he's done some very nice work in optimization, but also has been recently looking at biases in machine learning model. And he just received or recently received and is coordinating a large European project on that topic. So it's very exciting to have him here to tell us a bit more on the topic.
Thanks so much for having me.
Stage is yours.
It's a real pleasure to be here, and thanks so much for the invite. So this sits sort of uncomfortably in between the session we've had yesterday afternoon on the ethics and legal aspects of machine learning and the session which we've had this morning on the mathematics. Because in some ways in mathematics we often push towards solving problems which were well defined sort of 100 years ago, sort of such as optimization problems of various sorts. Whereas the sort of ethics and law sort of communities often focus on problems which they don't define very well. So here we try to sort of define some of those problems we've heard about yesterday formally, and then try to prove some theorems. I'll skim on the proofs, certainly, and actually on most of the theorems, but to sort of set this in context. So yesterday we've heard several talks about the regulation of AI, and especially the upcoming regulation of AI. But I think that it's good to sort of start with the sort of looking back. And the looking back really is that there are a lot of regulations which apply to AI already. And at least sort of going back to the Civil Rights Act of 1964, there are a lot of constraints on what the state can do in terms of the provision of the services of the state, and more recently, what businesses can do in terms of discriminating against some subgroups of citizens. So both in the US and in Europe, there is a long history of this civil rights legislation, which essentially is centered around two key concepts. One would be equal treatment, and one would be equal impact. And so sort of much of the talk is about equal treatment and equal impact, and about the actual sort of trade-offs you can strike between the two. It should be said that also sort of the subsequent years have brought regulation, and so sort of notably in Europe, some of the strictest regulation of AI which is already in force comes from GDPR, the General Data Protection Regulation, which many of you are aware because you need to click on some sort of acknowledgement button in all kinds of forms. But essentially the GDPR, among others, sort of requires certain amount of explainability of algorithms processing personal data, bars profiling of individuals, and many other things. The upcoming regulation will be much more detailed, and in the European Commission, the approach to it is sometimes known as the risk-based approach. So what this means is that sort of there will be some applications where the uses of AI are forbidden. There will be some applications of AI where you can do whatever you like. And there will be some uses of AI which will be regulated, and that's where this talk focuses on. So sort of if you can see the small font, essentially anything related to consumer finance, anything related to HR automation, most of safety critical systems, much of biometric systems, and anything related to the administration of justice will be classed as these high-risk systems and will have special constraints put on them. And in the rest of the talk, I'll touch upon some of these examples of applications, and I'll try to explain what we think would be good definitions of the equal treatment and the equal impact, and how to prove that your algorithm actually satisfies those definitions. So the big picture is that somehow you have your AI system and you have many users, and after some time the output of the AI system leads to some actions by the users, and then you observe the actions of the users, or at least some aggregate change of state as a result of those actions, and you make use of this again in some subsequent retraining of the AI system. And in the grand scheme of things, we're essentially saying that the equal treatment is concerned with the single use of the AI system. And that's what sort of 99% of the current work on fairness is about. And that maybe there is a sort of at least as important and interesting concern, which would be the equal impact, which would model the repeated interactions with this AI system. So for the equal treatment, I guess that you may have heard about the COMPASS system. So it was mentioned briefly yesterday, but essentially in the US, many states, including the state of New York, the state of Florida, state of Michigan, and some others, use a system in the sentencing in courts that tries to forecast the time to reoffending. And it turns out that for the various ethnically defined subgroups or racially defined subgroups of the US population, the error in this forecast is very different. So when you look at the time of reoffending in reality and the time to reoffending in the forecast by the system, if you're an African American, you will have a substantial error in this forecast. And as you can imagine, this error is one-sided, right? So it overestimates the sort of propensity to crime for the African Americans, and it underestimates the time to the actual reoffending, and it underestimates the propensity to crime in the white Americans, right? So this is a particularly sort of a touchy example because it's genuine life-changing decision made by an AI system. Fortunately not in Europe yet, but maybe with some more regulation, such systems would be arriving in Europe too. And this is a subject of a substantial amount of literature. So sort of there would be maybe 500 plus papers which try to propose systems to deal with this sort of a compass time to reoffending problem. But our original contribution here is that we see it precisely as this forecasting system, whereas essentially the whole of the community sees this as a problem in classification, where they get 10 classes of risk and then assign this class in terms of the risk. And we have tried to model this as a linear dynamical system identification problem with some events. And we have shown that you can apply some hierarchies of convexifications and you can solve some regularized problems where you can guarantee that the error will be the same across many subgroups, for instance, ethnically defined subgroups. And so sort of we have this sort of two broad approaches, the one we took here, and which is, I think, a small minority, where we changed the objective function in the training problem. And then the sort of a majority, as exhibited by many toolkits, including the IBM AI Fairness 360, where you essentially pre-process the data or reweight the data. And my claim is that sort of the reweighting or the pre-processing of the data is very difficult. Notably, when you have overlapping subgroups, there may not be any combination of weights which would be compatible with the sort of data you would have. So sort of in principle, we claim that the use of the regularizers is much more preferable as long as you can get global convergence guarantees for the algorithms we are using. And so far, we are using this in relatively limited cases where we have global convergence guarantees. But maybe, hopefully, eventually, we could make use of the material shown here in the morning by Jérôme or some of our own work in this direction of proving global convergence for broader classes of functions we would be optimizing over, and that way making this sort of putting more terms into the objective approach feasible more broadly. So in terms of the actual results on the Compass dataset, this may be hard to read if you have seen this for the first time, but essentially this compares against about a dozen other methods proposed in the literature. So here, this bottom plot shows that what we call AI Fairness 360 is the best method out of the many methods implemented in the AI Fairness Toolkit. And then these plots present a comparison of what we do using the regularized system identification methods against what the state of the art is. And the lower the better, and we're mostly lower. So that's a line of work which is joined with Bob Shorten, Chuan Zhou, Slava Kungurtsev, Fabio Vito Di Fonso, and many others. And we have some papers online if you want to know more. But for the second part of the talk, I would like to mention the equal impact. And I think that's much less studied, much less sort of up against the wall subject, and hence maybe more interesting. And so sort of in this picture of the closed loop view of the AI system, we would like to guarantee that the AI system across these repeated uses by the users has some nice properties, right? And I'll get to the nice properties shortly. And this is something we have been publishing a lot of papers on since maybe 2017. And the prototypical application to maybe keep in mind is from this paper, which is quite recent. And that's credit scoring, right? So when you have a bank, you would like to make credit decisions, right? And essentially, the bank currently uses some system of credit scoring and some affordability criteria. And we argue that those are not really independent, and that if you make the extreme case of this equal treatment happen, you could essentially say, I give the same credit limit to everyone. I give the same loan to everyone. But this wouldn't work really, right? So if you give $1 million loan to a person who's making $20K a year, very likely they will default, right? And this can make them unhappy forever after. And if you give someone who's making multiple $1 million a year $1 million loan, that's okay, and they will repay that okay, hopefully, right? And so sort of what we are showing here is that sort of this equal impact could be looking at what happens if you ask for the loan repeatedly. So you don't ask for the loan once, but for instance, in terms of the credit card, you are asking for the loan effectively every month, right? So sort of the bank can increase your credit limit or it can decrease the credit limit, and you have this repeated interaction really sort of playing out quite vividly. And in this setting, our claim is that a good measure of the what happens sort of over the many interactions would be the average default rate across the subgroup, right? And if you would like to sort of see it that way, we would like to equalize across the many interactions with this AI system, sort of which does the credit scoring and the affordability checks, the default rates across the subgroups, right? And the banks are essentially based on sort of a risk assessment. So you have to sort of account with some risk of non-payment, because otherwise the risk-free assets wouldn't really have any, right? And so sort of essentially, there is a lot of mathematics which goes sort of between the pictures and what happens. But essentially what we are doing is that we model this as some nonlinear dynamical system with these users being represented by some probability functions which give you the responses based on what you have as the output at the time and some state, right? And you can then reason about these nonlinear dynamical systems under uncertainty using a concept which is sometimes known as the iterated random functions. The iterated random functions essentially are a lot like a fixed point, where you would apply the function repeatedly and you would study where you end up in those iterations, except you have many such functions and you sample those functions randomly. And the key result or criterion in the iterated random functions is that if you have contraction on average, you can get a unique invariant measure. And if you can get a unique invariant measure, you get the existence of certain limits, including some long-term averages of the allocations, or long-term averages of, in this case, the average default rate. So you can produce conditions on the AI system under which you can guarantee that you have this behavior in terms of the weak convergence to a unique invariant measure for the dynamical system. This has many applications. So the application we have just had published paper in Automatica on is related to load aggregation in power systems. So that's something people have been talking for a long while, but for the past 2 years, you can actually get a Tesla virtual power plant if you live in California or Texas, and they are planning to roll this out sort of beyond. In California, about 1/4 of the regulated load would actually be down to some load ensembles like this. And in many countries, such as Ireland and the UK, this is now being actively used to sort of manage the flexibility in the power systems. And so sort of on the technical side, the major difference here is that you have some very nonlinear filter, which is down to the losses in the power system, in the power transmission. And so here you can again model things somehow probabilistically, but now you have some iterated random function system, which has much more complicated sort of mathematical properties, because you no longer have this and this linear and stable, which made the earlier analysis easier. Another application for which we have a lot of these formal definitions and theorems and proofs relates to two-sided markets, and that's sort of some area where Jerome, as colleagues, have won Nobel Prizes, and where you may interact with those systems sort of on a daily basis in Airbnb or Uber without really knowing the mathematics behind that. But again, we are sort of showing how to set up the controllers in these cases of sort of much more complicated closed loops, where there would be one side of the closed loop sort of modeling the demand. So these could be customers seeking a ride, and one side of the market sort of modeling the supply. So these could be the drivers you would like to incentivize to get on the road, or maybe get off the roads if there are not enough customers. And so sort of the summary of the results in this direction is that actually there is nothing like a small gain theorem in this direction, because you need both this and this to be stable in order for the whole system to be stable. So we have studied many loops like these, and we have results. So this will be some of the few theorems here. But even for these sort of relatively complicated interconnections of these nonlinear systems under uncertainty, you can get theorems. They are easier when you don't consider the delays between the sort of sensing and the action of the control system and the actuation by the people. And they get more complicated when you consider the delays. But in all cases, they essentially suggest under what conditions you can show the unique invariant measure exists for the closed loop, which buys you all of these sort of nice things, such as every driver getting the same amount of jobs in expectation over the long run, which is certainly not the case. There are well-documented studies where sort of female drivers and minority drivers sort of do much worse than the white American drivers. And the final application I wanted to mention, a minute over time, is related to social sensing. So when you ask people to sort of tell you things, and you base some decisions on the outcome. So this could be related to asking people about the state of the road congestion or about them sort of getting tested for COVID. But the general point is that it's hard in this case to assume that the closed loop stays constant, and because sort of people change, their sort of status with respect to COVID changes, and their response rate changes, sort of for instance, day and night or such. And so in this paper, the motivation comes from the social sensing, but the technical results extend what we have been doing before in terms of allowing for some changes to the system. And then this gets even more difficult in terms of the analysis, but at least in the sense of some sort of a perturbation analysis in terms of showing that small changes to the parameters of the system won't lead to terrible changes in the unique invariant measure and will maintain its existence. That's something we have shown here. And I think that's sort of a fruitful direction for further research. And I should like to say that that's, again, sort of based on fantastic collaboration with authors in Dublin and London and Passau and Australia. And now we hope to do much more of the same in sort of a largish consortium, which includes CTU, NKUA, Technion, Athena, Imperial, IBM, Workable, and Data.io. And that's all I have. Thanks so much. Mm-hmm.
Oh, and I was working. So on one of your slides, you mentioned you have a people in the loop.
Mm-hmm.
Do you feel, what kind of model do you use for people, and do you feel, is it sufficient for people making decisions about? Or
Well, that's a very good question. So what we essentially use for the decision making is that you get some state, and we look at the state and of the environment and the state of the person, and based on that, sort of usually the difference of the two or some function of the two, we have a probability function. And the probability function tells you if the difference is this much, the probability that the person does A or B or C or increases the something from A to B is this much, right? And this in some ways is quite generic as a model, but obviously how to fit those models to the actual sort of a population is a sort of a big open question.
But do you fit them? Like, do you fit them to real data, or?
We have tried some of this, and for instance, in the transport engineering, this is actually like state of the art, and it's sort of covered by a stack full of manuals called the Highway Capacity Manual, and people would tell you how to do this. In many other fields, people don't have that sort of institutional sort of process for coming up with these models, and the model calibration is often done. For instance, eBay or such like, they would have quite detailed models, but it's not something which is available out there sort of for anyone to download and access.
Okay, thank you very much. Any more questions for Jakub? Please.
At the beginning of the talk, you talk about dividing people into subgroups. Is this algorithm as biased towards specific, like the division of the subgroups? Is it like general, or do you decide in advance which subgroups you are divided people into?
Right, so sort of generally all of these algorithms are not aware of what subgroup you belong to. So those subgroups are based on what's called protected attributes, and sort of the algorithm wouldn't have access to the protected attributes. But in order to evaluate whether the algorithm is fair or not, you would like to sort of evaluate this with respect to some subgroups, and the subgroups come in the data, which in the case of the Compass data set were obtained using freedom of information sort of requests to the courts by ProPublica, by a sort of advocacy group. So sort of we generally receive this data. We don't use the data in the running of the algorithm. We use the data only to evaluate the fairness of the algorithm sort of post hoc.
Okay, thank you very much. Let's thank Jakub again for... And the next talk by this session, we are very excited to have Patrick Perez here. So Patrick is the head of the research at Valeo, which is called Valeo AI. Valeo, as you probably know, is one of the global automotive companies. And Patrick and his team have been doing very exciting work on making autonomous driving possible, which he'll tell you about. Just to tell you a little bit more about Patrick, I know him for a long time. So before he did some very exciting work at Technical and Microsoft, and he was a senior researcher at Inria, even before that, Inria. And today Patrick will talk about safer driving AI with limited human supervision. I'm very much looking forward to his talk. Patrick, the stage is yours. Thank you for coming.
Thank you very much. Okay, let's see if it works. So I'll talk about mostly perception for driving. And I will start with these videos, so there are plenty of them in the same screen. They are essentially some of our cars or platforms traveling across long distances or in urban environments. You see also some of the technical views. And what it takes for these cars to do this is, of course, lots of AI, hardware, software, and good sensors. And you see actually them here. I'll say a few more words later on them, but essentially you have laser scanners, also called LiDARs, cameras, and radars in particular. As I said also yesterday at the panel, one of the reasons why we care about assisted driving and autonomous driving is, of course, to make transport and mobility at large way better, safer, more efficient, etc. But when you think about it, in particular in terms for the people doing robotics, it's a bit of a crazy robotics problem because, of course, it embeds machine learning, but with limited resources. It has to function in real time. It's a super safety critical. It has to operate in an extremely open and unpredictable world with other agents, including vulnerable ones. And a very specific thing as well is that a car is on the road for more than 10 years in average, so it's not a mobile phone. So we have to take this into account as well. And one of the challenges with this high level of automation, so-called level 3 to 5 of driving automation, is that there are many different conditions where a vehicle can operate, and the statistical distributions, they can even change across time. So lots of different regions, different weather conditions, different driving situations, etc. And something you ideally don't want is a car, an autonomous car getting a bit perturbed by the sun glare, as you see on the left, or heavy fog, or on the right, what you see is a real example of a fisheye camera of ours, which is at the bumper level, so it's extremely exposed. In this case, it's all soaked, and it, of course, makes perceptions harder. So in order to try and mitigate these problems, we can do a number of things. The first one, and it's been a recurring theme in the past today and yesterday, which is to have more training data, whether real or synthetic, and from different sensors also. And in particular, one can try and make as much as possible out of unannotated data, what we call raw data, including by domain adaptation, also supervised learning, which I'm going to talk about today. Or you can try and annotate partially automatically this data. The top right example is actually from a collaboration with Tomasz and other people at CTU with point cloud annotation. But of course, it's very important to test these systems thoroughly on tracks, on roads. So you might get a glimpse at that for those visiting tomorrow, Valeo. And another aspect, which is, I think, very important, is the ability of the system to assess itself, its confidence. I'll say a few words on that. And at the end of the day, we know a lot about the rules on the roads and the rules of the physics. So there is a lot of knowledge that we should try to, of course, incorporate in our systems. And what you see at the bottom left is one of our recording cars in Ireland, and at the bottom right, it's radar signals, which I will say a few more words about. Talking about sensors. It's really important to have multiple types of sensors which are complementary. Here, what you see is the Valeo sensor suite. It's fairly classic in the diversity. You have, in particular, the cameras, whether the fisheye cameras, which are around the car, or the front cam, which is here. But you have also LiDARs, including these recent ones we have for near field. Our Scala is our own product. What is important here is that these sensors here are already produced at scale and deployed on personal cars. So these are actual products. And these are the one you saw in the video previously. So what is I want to highlight here is the complementarity of the different sensors. So the cameras and the laser scanners are pretty well known in the computer vision literature and community, and you see a lot of them in the conferences. Maybe one which is less popular or less investigated at the moment, and we like it very much, is the radar. So you see here raw signals from radar. It's essentially a spectrum of energy, and you have different views because you have three different axes. The distance of the object, the angle, the azimuth, it's called, of the object, but also the Doppler, which is essentially the relative speed of the object with respect to the sensor. In this case, the sensor is static. So it's not very easy to decipher this data, but it's something that we are trying to do. And actually, 2 years ago, we proposed this annotated data set where we actually segment precisely in these weird representation objects like a pedestrian, cyclist, and car. And the way we did it is using another modality. So it's yet another example of cross-modality automatic annotation, where we have an automatic object detector in the videos, and we have off-the-shelf, very powerful such detectors. And using these detections, then we transfer them automatically, knowing the geometry, into the radar signal. Then we are able to track the objects in the radar signal and to segment them precisely. And you see some examples here where these little things here are annotated objects. Okay, in the different views. In this case, it's a range angle and Doppler and range Doppler. And once you have this data, then you can train an actual system to segment objects in raw radar data, which we did the year after. So what you see here is what we call the radar cube. At a certain instant, you have a sequence of those, and you can extract different views, 2D views, 3 of them from the cube. And then you can design and train a convolutional neural network in order to then decode or detect or segment different classes of objects. And this is what you get here. And of course, it's not very easy for our eyes to recognize here, but I can tell you that these are actual pedestrian and cyclist in the video. And this is just for the visualization. Everything is done only on the radar signal. All right, and another thing about radar is that nowadays we have new generations of radar, which are with way many more antennas. And they are called high resolution or imaging radar, and they can allow you to even get point clouds, etc. And we have released at CVPR this summer a data set where we have HD radar with camera and LiDAR, and with segmentation and detection of vehicles, and of segmentation of what is called the free space. So if you're interested, you can just check it out. All right. Now I'd like to say a few words about being efficient with the data, even if you have only partial annotation or no annotation at all. And again, it's very important. Collecting data at scale with cars, I mean, it's not cheap, it's not easy, but you can do that to some extent. But what is really annoying is to get the annotation. All right. So imagine that you have lots of such raw data with multiple sensors, but you have a small budget for annotation. So what can you do about it? One, I'm not going to go through the list, but one key concept and key high-level tool in machine learning is to transfer things. Transfer from things that you know well to things that you know less well. So across modality, across sensors, as I just mentioned earlier, across different domains of operation, across different models, even sometimes across different tasks. So this is very powerful, and I'll say a few words on, in particular on self-supervised learning and on domain adaptation. But I want to highlight another sort of thread, which I'm not going to talk about today, is to also generate new data annotated. So there is the classic way of simulating your environment. So people do that a lot in robotics. We discussed that earlier today. So a fully virtual environment with classic simulation engine, and you know everything, so annotation is not a problem. But also there are all the generative neural networks, which are also another way to, by training, to generate new scenes, and it's very powerful. And now you have more and more of 3D aware such models, which could be useful in particular for our applications in automotive. So getting back to domain adaptation that I want to highlight today. So domain adaptation is the setup where, I mean, first the problem is to try and reduce the gap between some data that you have at train time and data test and deploy time, which are quite different. So the terminology is that we have a source domain with well-controlled annotated data, clean data, and a target domain for which you also have data, but possibly without annotation at all, but you can use them at train time as well. And the two domains, they should have some structure in common, otherwise it's a bit of a waste of time. And the very classic example of this situation is when the source domain is synthetic simulation, and the target domain is real data. And in this case, if you take these classic tasks that we have in the perception of for driving, which is semantic segmentation, which is recognizing objects at the pixel level, if you train on synthetic data, then with a new synthetic view, you have a decent segmentation with your model, but it can be catastrophic as soon as you have a real scene. And of course, you don't want that in your car. So domain adaptation is how to do way better. And in the deep learning era, there is a very powerful idea, which actually was first used for classification, which is called adversarial domain adaptation, where the idea is to learn a model which builds on a representation of the input, which is task dependent, but which is domain independent. And a good way to align this representation between the two domains, the source and the target, is to use a discriminator with in the context of adversarial training. And so on this little graph here, you see that you have your main model, say image segmentation, but it could be something else. You have some annotated source data, and you can train the usual way with full supervision. But now you have as well target data without any annotation, and you are going to select some level of representation in your model. It could be at the input, or it could be close to the output, and you are going to train at the same time a discriminator, which task is to decide whether the features of the representation comes from source or target. And hopefully at the end it would be confused, which means that your representation is domain agnostic. And then at deploy time, you just run your train model on the target domain data. And for semantic segmentation, staying with the same example, and with you see that if you train your neural network, is the example I showed, on synthetic data, and then you run on the synthetic scene, that's fine. On the real scene, it's not fine at all. And one interesting observation that you can make is that if you look at the confusion at the pixel level of the classifier, so the entropy, it could be something else, then you see it's very confused on the target target example. And this is actually something that we did leverage in a work in 19 in an adversarial domain adaptation work. Then using the training example from target domain, we can then get way better segmentation with way less confusion, way more confidence at the pixel level. I'm not going to go into the details, just one example, qualitative example here with just 1 or 2 numbers. Doesn't really matter for today, but you can see here two scenes where you have before, if you don't do any adaptation, and if you do adaptation the way we proposed it at that time, and at that time it was it allowed us to push the state of the art by several so-called mean intersection of over union points, which is the classic criteria for semantic segmentation. All right, and this idea of adversarial unsupervised domain adaptation can be extended to multiple modalities. This example here, the task is semantic segmentation of point cloud, and we use the ideas to use both images and LiDAR. And the idea is that the domain gap between, say, synthetic and real, or between night and day, is not the same in the two modalities. For instance, the 3D structure is, the point cloud is fairly similar between night and day, whereas the images are very different, etc. So we have a cross-modality learning here, which I'm not going to explain, but it's essentially an extension of what I presented before. And on this example here, you see that in the day-to-night adaptation, with this scheme here now, for some of the, if you don't do adaptation, you might miss some of the objects that you recover here, and vice versa, you can have false positives, which are wrong detection that you can clean with the adaptation. And you can easily imagine what is the benefit of this. Another interesting aspect when doing unsupervised domain adaptation is that you can do what is called self-training. It's quite often is beneficial. The idea is that you have a first version of the model that you can then run on your unannotated target data, and this gives you automatic labels that you might want to reuse for the next iteration. But if you do that, you have to be careful to make sure that it's not too noisy, and it's important to be able to predict what is the confidence that you have in this first prediction on these unannotated images. So again, on classification here, you can measure the confidence at the pixel level, and then you retain only the pixels for which you are fairly confident as new auto labels for retraining or fine-tuning your model, and this is very, very beneficial. But here there is an important concept, which is the confidence. So or maybe I can show you here the benefit. It's very hard to see maybe on the screen here, but typically if you have a careful way to select what is confident or not, you see that here in green are the automatically labeled pixels that you retain for retraining. When they are green, it turns out that they are correct. If they are red, they are not, and there are fewer red pixels on the right. Maybe it's not striking visually, but it does make a difference in the performance. But the point here is how to assess the confidence. So there are classic ways, like I mentioned, the entropy, or you could look at the classification score for a classifier, which is a classic way. I'll get in a minute how to do better, but if you are able to have a good assessment of the confidence of your main estimator, then you can use that for rejecting or for predicting that a sample is out of distribution and you shouldn't take a decision, or you can, as I just showed, do automatic annotation, which is useful. And at a system level, or more even be taking a robotics kind of angle to things, if one of your modules assess itself as being very uncertain, then you can pass this information either to the next module or to the next instant, or you can rely on another sensor, etc. So confidence estimation on the fly is very important. And one thing we proposed, because the simple ways to assess performance or confidence are usually not very good, and typically deep neural networks are very confident even when they are wrong, and it's a well-known problem. There are other ways to deal with that, with calibration, etc. But the one I want to highlight today is to to learn another. So you have your main model here, which is trained and frozen. It gives some prediction, say for classification, 1 score per class. And the idea is to train another model on top of the features of this model. And this new model is an auxiliary object, and its task is to predict the confidence of the model for the given input. And one way to supervise this training is to, at train time, you know the real class, so you know what is the score for the real class, and you try to regress this with a classic L2 loss, and it's very simple and very effective. All right. I will finish by a few words about self-supervised learning. So training with no annotation at all has been discussed today, and including by Cordelia and yesterday for language. It's very interesting. In our case, what we have is a lot of data which are synchronized with different sensors, as I already said. And the typical case is cameras and LiDARs. And in these two recent works, one presented this summer at CVPR, and the other one of Antonin, who is in the room here. So it's a collaboration with CTU and Joseph. It would be presented at ECCV. We rely on this alignment to do self-supervised learning of useful representation of the input. So I will say a few words, or even no words, just images on the second one, driven segments. So again, we assume that we have cameras and LiDAR points which are synchronized in times and in space, and without any annotation, we are able to learn a semantic segmentation model that you see here, which has never seen ever a label. So it doesn't know anything about semantics whatsoever, and you see the type of results. Of course, it's noisy, but again, bear in mind there is no annotator behind. I'm not going to go through then I will leave that for questions or for discussions if you want with Anthony as well. One example where you see that the model has been trained on a certain data set, and now it's used here to segment other images from another data set, in particular with bad weather or nighttime. And you see this is on the right is column is ground truth, the middle one are what you obtain. The colors, which are semantically meaningful, are matched, but again, our model doesn't know about semantics. All right, and this brings me to the conclusion. One of the challenges we have already at the perception level for assisted and autonomous driving is that we have to operate in a large, in all the domains or in many different domains, and we like data or annotated data. And some useful tools, of course, is not only to have a variety of sensors, but also various ways of leveraging data with no annotation or little annotation, and also to make sure that we are able to predict the confidence of our model. Last point, which I mentioned already yesterday, is that looking outside of the car is good, but looking at the driver is very important as well. In particular in the case of autonomous driving, where you want to either take over from the driver or to disengage the system, and this is also a very important topic, and we really have no public data or little public data available, so it's a call for the community, and I will stop here. Thank you very much.
Let's take Patrick for the very nice talk. Are there any questions from the audience?
Thank you. Thank you, Patrick, for this excellent talk. I had one question. So you showed at some point the Valeo sensor suite, and my question is, do you... No, not really. Well, actually, perhaps at one point. No, my question is, normally we have sensor models for all these sensors, and do you still use them? And what is the role of precise sensor models in all these AI-related machine learning algorithms?
Okay, the models are very important for testing and validation in simulation. I mean, they are important for when you design the sensors, of course, but we use them a lot for the validation. So part of the validation is done in simulation, and for that you obviously need accurate enough models for your sensors, if that was your question.
Yes. but you don't use them as some kind of additional information in the model, right, to improve
Oh,
performance.
no, well, not actually, not precisely. Of course, the type of setup. It's, I mean, in the case of fisheye cameras, which is a very specific beast, and there are not many data sets apart from the one actually we have released 2 years ago, Woodscape. In that case, taking into account the very specific geometry is very important and the calibration, etc. But beyond that, the specifics are of course taken into account, like the radar, what is the wavelength, etc. But not to the all the way to the physical model at this stage.
Okay, thank you.
One more question for Patrick.
Thank you very much for fascinating presentation. My question would be, I believe, a little bit naive, but as a
they are the most difficult ones.
An expert, you can follow the development of the technology via the media, for example. This is the race for even higher self-autonomy of the driver of the car that drives itself, right? This is called, I believe, 3 to 5 levels of the autonomous driving. My question is, sometimes you can read in the newspapers, very difficult to assess, obviously, of some crashes or some failures of the technology. And this is not always clear whether it's already really about the technology or a driver's intervention. It might be a panic reaction or whatever. So in this regard, I was quite, it took my attention your appeal to that we need to do more, pay more attention to the driver himself or herself, because it's an important actor. So is this possible the way that you can elevate the technology and build the confidence and to build a trustworthy AI? That this is the holy grail.
So it's a difficult question, and just to make it short. So first of all the current accidents with fully autonomous driving cars, which are authorized and which are all prototypes, which are authorized in the world, are reported to the authorities and they are examined. And quite often it's the fault of other cars, so with human drivers. But it's really documented. Of course, with fully driverless thing, the question is different. If you have no wheel, no pedals, then it turns out that often you have a teleoperation behind. So you have, in a sense, another driver. What is the? I mean, the accidents we had recently with actually commercial cars with high level of automation are mostly due, as far as we know, due to an improper use of the system by the human driver, using it as if it was a self-driving car, and it's not. Maybe it was advertised this way, but it's not. But of course, we have really to look into that and to make sure that these still immature systems are well used. We'll see how it goes, and I think I said a few words as well yesterday in the panel about that. But the road is still long.
Let's thank Patrick again for a wonderful talk.
So I'll keep the mic then. It's my pleasure to introduce Joseph. Maybe no need for long introduction of Joseph in this place yet. So Joseph is a distinguished researcher at CIIRC here in Prague. He's also on a leave of absence from Inria in Paris, and we miss him. But he has a longer collaboration with these guys. He's also the head of the ELISE unit in Prague, among other things. And the last thing I will mention, because I did it with Cordelia, with the test of time prices, you also have 3 of them, 1 at CVPR and 2 at ICCV. So we are in good company today. And the floor is yours.
Thank you very much, Patrick, for a nice introduction. I understand we are late, so I try to be shorter than this. Yet I would like to tell you a little bit what I'm excited about currently in my research. And So I'll start with this video, and hopefully it will start playing it. So imagine now you are in a car and you get a flat tire, and you're far from getting help, yet you have a reception, so you can Google up and say, well, how do I change a car tire? We have a spare replacement. And this video comes up where someone is showing to you actually how to, what manipulation actions you need to do, narrated with natural language, explaining you what you need to do to change the car tire. And in fact, if you don't like that video, there are other videos with different tools, slightly different tools, and maybe different car models, which show you how to do the specific task of changing car tire. In fact, there are millions of these videos for different tasks in different domains, going from car repair, gardening, cooking, or healthcare even. So really, these instructional videos provide a very nice sort of test bed for learning from visual content together with natural language, because they are narrated, people explaining what they are doing on the video. And so we've been looking at this domain now for a while, and one of the sort of overarching goals would be, what if we could actually learn from this data, some kind of an instructional manual, which we can then go and apply in different contexts. For example, in augmented reality. Imagine that you can now automatically give instructions to a novice user how to do a specific task in a new environment, both maybe for home repair, but also actually this is in industry, you have often tasks which are automated, workers doing that, and you want to maybe at least check them. Have they completed all the steps in a particular assembly task? Another example is robotics. Imagine then the robot can go in and look at at some of the instructional videos and learn a new task and then do the task in a new environment, maybe because a person cannot go in that environment. So these are some of the applications which we would like to do, and I will show you some of the works we've been doing in the past few years in that area. And I will try to really sort of watch the time, so it's not too long. So the first one is really learning from video and language. It was one of the first works we did in that was actually identifying the individual steps of the task. So on the right here, you saw the automatically learned steps from the narration and the video, and on the bottom, actual temporal localization of these individual steps in the video. Yet these results was interesting. We could actually identify the different steps, but they were relatively small scale. These were learned from maybe on order of 50 videos of a particular task of changing car tire, and we were doing maybe 5 to 10 tasks, so relatively small scale. So one of the next steps afterwards were, can we really take this large scale? So we've downloaded and still one of the largest available video data set. Cordelia mentioned it here, it's called How to 100 Million, where we took sort of on the internet, you can actually download instructions for many different tasks on the WikiHow, and we took more than, I think, 10,000 different tasks and obtained more than 1 million videos for different for these different tasks, and in the end have more than 100 million clips. And what the goal here is now to learn a joint video and language model. So you see there is a video and language from these videos. So without any specific manual annotation, the model tries to predict for a given video the actual text narration. So you see at the bottom, it's learned with a contrastive loss, so it tries to also the narrations from videos which are sort of from different videos in that joint embedding space, it's trying to push them apart. And this actually works quite well. And then I'll just show you examples of what you can do with this. You can then do, and hopefully it will play here. I think I may have to click this. Yes. So you can now search in language, type glue, and it will find you other videos where people are gluing. And this is not using the language at all, the narration, just based on visual search given the language embedding. But you type glue wood, and it will find you examples of videos where people are gluing wood, cut wood, where people are cutting wood. You can even be more, so here you'll see cut paper. You get video where people are cutting paper. You can be even more specific. You can put cut paper in circle, and you will get videos of people cutting paper in circle. And so what's exciting about this is that we used to have to manually annotate different videos with different the labels, but here the natural language provides almost infinite label space because it's compositional, and you can search for any sort of composition of the given by the natural language. And in fact, and I will skip the details of the evaluation, but really given the large scale of the data set, it sort of can outperform models trained on manual annotation. So we've been, as a community, but also have been working on these sort of weakly supervised learning models from readily available data for quite a long time. And now we are seeing that these models can outperform manual annotations. So this is all online. You can even do the searches which you've seen. You can try it out yourself. So this was, you can use for other tasks. Cordelia talked about it. I'll skip this. So now we've seen learning from large-scale video and language. But in reality, the world is very, if you want to do physical interactions, the world is you need to go beyond just being able to describe or search videos. So this is an example of work with Nicola Manzart, who talked earlier about extracting from instructional video, which is on the left, and I will try to play it again. Input video, and on the right is the reconstructed motion of the video, but together with estimated forces shown as yellow arrows between the person on the ground and the interaction with the object. So we can estimate this from the video. It's set up really as a two-stage problem. First, we do estimate the person pose, the contacts, and the tool position in 2D, but then we formulate as an optimization problem where we minimize the reprojection of the video into of the sort of 3D estimates into the video, but subject to constraints which are by the contact motion model, full body dynamics, and force model. So, and this is, one can also evaluate this, also validate on a ground truth, but what we're really excited about, the part on the left, which is applying it to instructional videos, where now we can really estimate the interactions in 3D, how people are interacting with objects, and estimate the forces of these interactions. And why is this interesting? Is because then we would like to put this motion on a robot. And this is a more recent work from this year, and this is collaboration with, which I think was shown by Isabelle yesterday, where with Justin Carpentier at the Prairie Institute, where we would like to, given an input video on the left, really use that video to drive a manipulation action on the robot. This is difficult because the action is dynamic, so it's hard to actually learn this automatically by reinforcement learning. But what we do here, we use the instructional video to guide the learning process. We extract the 3D motion using what you saw just before, and then have a new method to align the simulated environments with the sort of input video. And then in the simulated environment, we can perform reinforcement learning and learn actual policy, which can be then run on the robot. And I will sort of skip the details of the method, more show you some of the results. We actually done it for several different tasks and several different input videos. And for each of those, we have an environment in which we can check that we can really learn the particular task, like the shoveling, hammering, or using the side here. One can evaluate, and actually what we can get similar performance to what's called, if you do the demonstration in the robot space. So just by learning the video, from the video, it's like if you were, which is the standard approach in robot programming, if you do it in the robot space. What's interesting is that one can do this, it doesn't really depend, because it's focused on the tool, on the morphology of the robot. So we can learn these policies for robots with different degrees of freedom or very different morphology, and it's still, one can sort of learn from these instructional videos, even if these are not humanoids. And it works similarly for different morphologies. And finally, what I would like to mention is, so in the end, still the policy which we learned was open loop. So we really learned it from the video and then transferred it on the robot, but there was no perception. So we would like to really now close the loop, and that's subject of the future collaboration which we have with Nicola Manzart and also Justin Carpentier in Paris and Toulouse, on really having now closing the loop and having robots observe the environments and sort of learning how to act on them with the perception. And here is an example of work which we have in this direction, where we would like to really give one or more input images to estimate the pose of the object in 3D in the environment, because here is the example. So in this case, we have a given cut model so that we can manipulate the object by robot. And we've developed an approach which combines deep learning with multi-view geometry, which I'll skip the details, but it works quite well for this task. So we have on the top is input image, middle row is predicted poses, and at the bottom is the 3D visualization given the single input image of the scene. So now it can really go and robot can manipulate these objects. These are different data sets for a competition on this problem. It works also with textureless objects, as you see here. And despite even occlusions, and the objects can be self-similar. There's a competition on this problem where this algorithm did very well, which was run now 2 years ago. And what's interesting that even this was only using RGB input images, it performs as well as if you have also the depth input, if you have depth sensing capabilities. And what I want to just sort of show you in the 1 or 2 minutes is some of the more recent results. One can apply similar method to articulated objects. So we are estimating here, given individual frames of the video, not only the pose of the robot, but also its articulation. So this is more degrees of freedom. We are expanding the space. It's not just 6-dimensional translation and rotation of the robot, but in additional articulation. And one of the very recent results which just got accepted to Robot Learning Conference, Coral, is that which you've seen so far, we require the model to be known in advance. So at training time, the method needs to know the models and it learns on them, and it can still take quite a lot of time. This is a step, is a new approach which does not require the models to be known in training time. So in fact, we have a large data set of more than 1 million images, 50,000 different scenes, where you have many different objects from a database of CAD models. And we learn a model, a deep neural network, which can then align new objects never seen at training. So this is really a step addressing one of the key limitations. We are very excited about this. So we have, at training, you synthesize this large number of images from a large database of CAD models. And at training, you see a new model here, the scissors, and you can estimate its accurate 3D pose in the image so that then the robot can go in and grab the object. And it does work. You can simulate these effects like occlusion and the variability of objects. So these are some of the examples from the test set, and it has never seen this object at training time. And so what you can do now, you can estimate in the video, you can estimate the pose of an object which you haven't seen at training time. And so now if a robot can come in and start manipulating these objects, and it's maybe somewhere later in the video. So I will finish with this. So we are very excited about learning from instructional videos and are also working on these different steps, both extracting these video language models, extracting more physics-based representation so that we can really interact and manipulate the world around us. Beginning to work on transferring these skills onto robots, which is very exciting, and also closing the loop with the perception. I thank you very much for your attention.
Is it working? Yes. Sorry. So thanks. It's been an impressive completion of your talk. But all the references are there for interested people. But yet, owing to this effort, we can take a few questions now.
Yeah, apologies for being fast, but I wanted to save some time for the coffee break. Yes, please.
So at some point you had some training using the images from, and you said it's not possible to do everything by reinforcement learning. and I didn't get exactly why, because you have this simulated environment, and it seems to be quite relatively constrained, and I thought you could maybe explore all the possibilities there. I'm not sure. How much does it speed up?
Yeah, it's a very interesting point. So one would think, we also thought, oh, this is going to be easy. We're going to do by RL, we'll solve our problem. But it turns out, so here the RL needs to work it really operates in the joint space of the robot. So this is, first of all, this is not an easy space to operate in, because it's, really what you're controlling are particle angles and velocities of the robots, which has maybe 7 degrees of freedom. In addition, you're optimizing the position of these objects in the scene. So the space turns out to be somewhat high dimensional, and the standard RL techniques are just not able to find a reasonable solution. So we devised, and I did skip the details, but what we combine is that we combine here sort of more standard optimization techniques, which are, so first we find a trajectory of the tool, which is easier because it's just, three-dimensional, and use the video to help to guide the process, because we have the trajectory from the video, and then use more standard optimization techniques to find, from robotics, trajectory optimization, to find the joint angles, and use those to steer the reinforcement learning, if you wish. But you are also surprised, reinforcement learning is not a magic bullet. Some of these problems are still hard search problems. Yeah.
Another question? Nope. Then I'll ask one.
Okay.
So, when I was in the movie industry, people were all excited about doing animation through mocap. So you reanimate a creature, which can also be of a different type of morphology, etc. So, can you see any applications in this field of content creation, whether it's for games or movies or whatever?
Yeah, definitely. I think it's interesting. So it's some of the tools in robotics, and Nicola can say more about this, are also used in graphics. What's interesting, though, is that when we started to talk with roboticists like Nicola, is that it's not, you can't really easily transport from the graphics to robotics, because when you have a real robot, you have to really, and Nicola talked about it, respect the constraints. And whereas for animation, the problem is that it has to look good, and whether you are the model is actually using forces which are unreasonable, like much more what a human could, doesn't matter that much. So in some sense, I would say yes, and maybe the problem is easier because you don't have to respect the real-world constraints. But of course, it's a very nice application area as well. Yeah.
The session, and you can ask over the coffee break, I'm sure. So thanks again, and I will pass the mic to the organizers.
Thank you all for staying till the end of the last scientific session. According to the schedule, we have to start the closing session right now. So my recommendation, I don't know whether Veronica will accept it. Veronica will accept it. Let's make the closing session right now. And then we can move upstairs for the coffee break, and we can catch the round trip through the facility later. So I think we can save a lot of time by making the closing session right now. Are you okay with it, all of you? Let's do it. Okay, Veronique, please calm down. Peter, calm down. And let's start the closing session. Don't be afraid, the coffee will be hot also in 10 minutes or 15 minutes. We are guarding the room, so nobody will steal the cakes, so I think it might be useful to close the workshop right now. So, I have the pleasure and honor to open the closing session. And I'm giving the floor to Veronique.
Thank you. Hello, everyone, and thank you so much for staying in the room and skipping for a while the coffee break. So for those who weren't here yesterday, I will just quickly introduce myself. I'm Véronique de Bord-Lazaro. I work as science attaché at the French Embassy here in the Czech Republic, and we're part of the organizers of this workshop. So the wrap-up session, the idea was to, first of all, try to give you some information about the existing mechanisms of support for Czech-French cooperation. So I will give you some information on that, and my colleague Petr Kaiser from the Czech Ministry of Foreign Affairs will pursue. And the second part of the wrap-up session, which I guess is at least as important as that, was also to discuss quite briefly, but at least have some ideas of what will come next. This is the first workshop, the first Czech-French workshop on AI. We're really happy that it could take place. We're very grateful to all our partners and in organizing this workshop, but we don't want it to be the first and last thing that we will do in AI between the Czech Republic and France. We see a lot of potential. Of course, it's difficult after 2 days. We've heard a lot of people talk, excellent speakers. It's hard to have already a full plan, a full-fledged plan to roll out. But at least we would like to have some ideas for development. So I will also again say a huge thank you to our colleagues from all the partner institutions that have made this possible. At the CVUT, there are so many people, but mainly I would like to thank Professor Marzik for his support, Josef Šivec, who's been amazing, and Eva Doležalová for great help. I think you can give her a round of applause, all of them. At the Ministry of Foreign Affairs, Petr Kaiser, so thank you so much for all your support. And also in France, our colleagues from the Ministry of Higher Education and Research, Stéphane Canu, and at Inria, Isabelle Erland, who unfortunately could not be with us today. So I will, this is online, oh, this is on already, that's great. So as I said, I will try to be brief, but give you an idea of what we're doing mainly at the embassy to support Czech-French cooperation. I will not keep the suspense too long on one thing, is that there is currently no Czech-French research fund as such. So this is one of the things that we will try to develop, but no suspense, there is no such thing for the time being. So I hope, nope. Should it work? Yep, it worked and then didn't work. I'm really sorry. It's on. Okay. Oh, you're doing it. Thank you. Okay, so just one also quick thing. Usually people don't know who we are and what we do. So I wanted to mention who we are at the French Embassy, the French stakeholders in the Czech Republic, to support scientific cooperation. So we're a small team at the Embassy and the French Institute in Prague, at the Cooperation and Cultural Action Department, and our job is to be the contact point for researchers and academics, both in France and the Czech Republic, who have bilateral projects between both countries. We also do a lot of promotion of French research, and our third task is to encourage the development of student mobility. So we promote higher education in France and student mobility both ways. One other very important stakeholder that I wanted to mention is, because it's quite unique and it's very uncommon to have this in a country, in a foreign country, is the CIIRC, which is the French Research Center in Humanities and Social Sciences in Prague. So it's a real joint research unit between the CNRS and the French Ministry of European and Foreign Affairs. We had some specialists in social sciences yesterday during the workshop. The CIIRC, as I said, is quite unique. It's a real research center that organizes seminars, that has researchers. It's really a platform that can be used also to encourage mobility of PhD students and master students. And they cooperate a lot with Charles University and the Czech Academy of Sciences. If you can, thank you. So at the embassy, we support all endeavors to encourage cooperation between the Czech Republic and France, but we do have some priority topics that are in line with the embassy's action plan and also the EU priorities. And those topics are, not too surprisingly, energy-related issues and the development of a low-carbon economy, digital sciences, that's why we're here today, also cooperation in special research, especially on applications, and finally, cooperation in security and defense. So you have here listed all the type of activities that we run. We operate a number of funding programs, and those are the ones that I will mention tonight. Of course, the slides will be made available afterwards, so don't worry too much if you don't remember everything. Eva, can I ask you to? Thank you. I'm really sorry. So here you have a presentation of all our existing tools. This can really be seen as a toolbox for researchers and also PhD students. As you can see, we're really big fans of Joachim Barrand because all our support tools are named after him. I hope everyone knows who Joachim Barrand was here, right? You all know who he was? Maybe not. No. So he was a he was a geologist, and a French geologist who did most of his work in the Czech Republic. If you go to the National Museum on Václavské náměstí, you will see big collections of rocks that were given by him to the museum. So as you can see, our tools they have a progressive nature. So we start by supporting bilateral workshops, typically that one, that's the first one. I hope there will be other ones. But we also do the same in chemistry, biosciences, nano and advanced materials, and nuclear sciences. Then we have mobility programs that support networking between France and the Czech Republic. I will come back to that in a moment to give you a little bit more information. And also we support PhD students traveling to visiting France or the Czech Republic. So thank you. So a quick word about our two mobility programs for researchers. Barrand Mobility, which is a really bilateral programs between the Czech Republic and France that is supported both by the French Ministry of Higher Education and Research and the Mochamoteur here, so the Ministry of Education. And the idea is to allow two research teams from the Czech Republic and France to deepen their cooperation on a specific project. It strongly encourages young researchers to participate. These are 2-year projects. It's really seed money. So we can support mobility both ways. You have the amount that is dedicated. It's a small amount, but it can help trigger new cooperation. There's a yearly call. The next deadline will be next year, June 2023, and we support about 10 to 15 projects every year between both countries. The other one that I wanted to mention, the other program is called PHC Danube. Even though the Danube doesn't go through the Czech Republic, it's still called like that. It's a regional program that is a complement to the previous one I was mentioning, and it's based on a partnership between several countries, so Austria, the Czech Republic, France, Serbia, Slovakia, and newly this year, Montenegro and Bulgaria. And the idea is to enable researchers to create a network to facilitate applications to EU funding. So it's really, again, seed funding to be able to apply to bigger research projects. Again, we support mobility. You need to find 3 to 5 partners in the countries that are involved. These are 2-year projects, and the next call should be launched in November, 2 months from now, November 2022. I think second to last program is Barrand Fellowships. So this is our mobility program for PhD students. So I don't know if there are still PhD students in the room, but it can be of interest to them. Again, this is a partnership between the Ministry of Education of the Czech Republic and the French Ministry of Foreign Affairs. And the idea is to enable PhD students to apply to go and either spend a short-term stay in France or the Czech Republic from 1 to 3 months, or to do a longer-term mobility in the frame of a co-tutelle. So a co-tutelle is when students get 2 degrees from both countries. And in that case, we support, we offer mobility grants for 5 months per year over 3 years. You have here the amount of the grants. It's open to all disciplines, like all our programs, but again, there will be, there is special attention given to programs in energy, connected to energy, environmental sciences, and IT. We have about 20 to 30 laureates every year. This year, 22, we're on the lower side, and the next deadline will be February 2023. We always organized webinars to explain the program in details to the students who might be interested. And finally, I mentioned that we support the promotion of science. We have been running for 30 years now scientific prizes at the embassy. So the idea is to award the best young Czech researchers. It's been conducted under the patronage for now 29 years, almost 30 years next year, of Jean-Marie Laine, who's a Nobel Prize in chemistry. We have 6 categories, and there is 1 category in computer science, so the Joseph Fourier Prize in Computer Science that we are running in partnership with the company Atos. So the students that participate in this national competition get a financial reward, but also a scholarship to spend a month in a French research lab. So if you have students, good students, you don't need to have any cooperation with France yet. It's just academic excellence that matters. So I would strongly encourage you to enroll them in the competition. And I think I have one last slide. These are not embassy-run tools, but I wanted to mention 3 other opportunities that you might want to look into. The first one is that in 2020, the CNRS and the Czech Academy of Sciences signed a framework agreement to facilitate the support of jointly run projects. Again, this is not that does not support research itself, but it supports mobility between France and the Czech Republic. Especially to explore new fields of research. So there's a call that is open every year. I think there's one that's still open right now, running right now. And I would strongly encourage you to look into that if you want to develop a new network. Inria also offers interesting possibilities for stays in France. So or in other countries, and especially would like to mention the Inria international chairs that enable international researchers to go and spend some time in a project team at Inria. And finally, a small program that is run by the French Ministry of Higher Education and Research. And the idea is to encourage the participation of either French researchers to seminars or conferences that are held in Central Europe or Eastern Europe, and vice versa. This is a yearly call. The process is pretty easy to follow, so I would encourage you to try it if you're interested. And the last slide, thank you, it's just our contact details, so please feel free to contact us anytime. I'm also talking to the French researchers when you're coming to the Czech Republic, come and say hi. We're usually friendly, and we'll be happy to learn more about your projects. And you have also links to our website with all the information that you may need. So that will be it for me. I hope I wasn't too long. I tried my best.
Thank you very much, Veronique, for telling us all about these collaborations. I'll be next in this, and I'll say a little bit about sort of science and sort of what could be. Also, we discussed a little bit what could be the next steps. One possibility would be, if to organize another workshop to maybe make it a little more focused on one particular topic. So we discussed that a little bit with some of you. Already. One topic which sort of scientifically seems to be touching on almost all areas which we've seen here are these big foundational models, large-scale models. They are made the major leeway in language already. They are very interesting from ethical standpoint because of their emergent properties. From the theoretical point of view, they are sort of being also analyzed. Lots of analysis needs to be done on them, and they are also explored for, being doing the mathematical proofs. I know the group here is involved in a big science project. In robotics, of course, there hasn't been that much work yet, but I think like the memory of motion, I think is a step in that direction, which we've seen to have like a foundational model for embodied perception and interaction. And of course, in computer vision, we saw in the talk of Cordelia where multimodal is very important in this. So one potential kind of topic which seems to be touching on almost all we've seen here would be these sort of large-scale models on this, what I've seen. But I'm very happy to discuss with other suggestions from any of you what you see interesting. Another thing which came up is because a lot of people here also have collaboration with Germany. Like, wouldn't it be great to also involve some of our German colleagues in this area? So one possibility would be to look into that direction, like organize on more specific topic and also invite colleagues. So I'm very happy to discuss on any of this, but it's been a really wonderful workshop. Thank you very much to all of you for coming here. Many of you are my current or former colleagues. It's been really great to see you here, and thank you very much again. Thank you.
Thank you very much. I will pick up on the point raised by Josef. Actually, there's been a number of discussion on the margins of our workshop on how we can proceed and build on what we have actually analyzed and discussed during the 2 days. And I think there is really a lot of potential for that. So we have come with a proposal together with Professor Magic, with Monsieur Leroux, with Fabien Levoyer and others, Veronique, that possibly we could elaborate a kind of a very short document in which we can conclude some or feed up some of these ideas and share with you for your comments, for your consideration, suggestions, and later on we can get together, those who are interested via online, to discuss some specific topics, because in my view it would be really important that we ensure a process that would really build on some specific issues. We are ready to work on that as the Ministry of Foreign Affairs, together obviously with our counterparts. I know that there has been already thanks already, but I can't resist really really thank to our partners. We have been working with CIIRC and with CTU for some time, but I have to say this is the very first workshop that we even have developed our own jingle, which was very funny. I really like it. I believe that all the preparations were very professional in terms of technical support and so forth, which is to be thanked to Eva and Marcela and other people. But as well, I think the workshop was very well prepared in terms of substance, thanks to Dr. Shivitz, to Isabel, and many other people. I really appreciate that. So once again, thank a lot everyone from the CTU. Thank you very much, Veronique and others for that. And let me really assure you that the Ministry of Foreign Affairs is really ready to support the French-Czech collaboration in this strategic technology. Before I just finish last point, I don't want to speak too much about concrete instruments that were actually addressed by Veronique, but there is a call for proposal to be launched, I believe, next month, which is administered by ANR, which is Agence Nationale de la Recherche, and this scheme is called CIIRC. The call is actually very well, I would say, very well suitable for technologies related to artificial intelligence. We will provide you all the information at our website and might be shared our document I referred to at the beginning. So once again, thank you very much. It's been a great pleasure to work with you.
So, ladies and gentlemen, we are at the end of the closing session, and I am very glad that we had a very nice, high-quality AI workshop, Czech-French workshop, which did happen after 3 years of preparatory activities. And I would like to thank to the people who enabled this workshop, namely to Veronique, for her persistency for 3 years over the pandemic period to prepare systematically the workshop. And the result is here, and I'm very glad. So thank you very much. And I have also to say that the support from the French embassy side was all the time tremendous. So also thanks to Mr. Ambassador. Tell him thank you on our behalf. Thank you very much. The other person who was also very persistent on the Czech side was Peter Kaiser from Ministry of Foreign Affairs. They played a very interesting game, forcing us to organize this workshop for 3 years. So Peter, thank you very much. It's also your child. Yeah, and I'm very glad that this workshop was not only, let's say, good on political or administrative level. It was really a scientific workshop with many, many interesting papers, discussions, communications, because also communications belong to this. And as a matter of fact, I would like to thank to Josef Šivec from CIIRC, who did a lot of work to bring people together, to bring relevant people together, and to organize the content. So the content quality was caused by Josef. Thank you very much. And at the end of the day, I am bringing away from this workshop 3 tasks for myself. First of all, I have recognized that there is no bilateral funding for Czech-French scientific cooperation. So my task number 1, I am member of the R&D and AI Council. Together with Veronique and with Peter, we will try to do our best to ensure that at least some seed funding for bilateral cooperation will appear in the forthcoming 2-3 years. You know, financial planning is not for a week, not for months, but it counts in years. But still, we will start to make some efforts in this respect. Second, you know, we have a very good relationship with DFKI. That's our really best partner who helps us since the very beginning. DFKI has a very good relationship with Inria. So there is a time to complete this triangle. And my task, and I hope Josef will help me, is to enhance the cooperation with Inria. And the CIIRC Inria or CTU Inria cooperation should become the backbone of cooperation in the field of AI and computer science in broader meaning of this word. Because without such backbones, it's difficult to organize workshops, it's difficult to organize joint projects and whatever. So the other task for me is to force Josef to enhance the Inria CTU cooperation and to complete the triangle. I think that DFKI will be not against it. Tilman Becker is saying, confirming this, okay, and if here is Wolfgang Walster, he would say the same, I'm quite sure. So, and the third task is to be responsible for the fact that next workshop will follow. We cannot stop with this one because it was very successful and a lot of let's say, ideas in which areas we could continue together appeared. Let's focus our attention just one or two and organize something similar, maybe next year, maybe 24, but it's too late. It's not, we will see. But let's continue in these workshops because they are very useful for intensifying Czech-French cooperation. That means to intensify cooperation inside EU because many projects in the past, and Mr. Leroux can confirm it, just appear based on bilateral cooperation. So at the end, I would like to thank also to the people who helped to organize the smooth organization under the leadership of Eva Doležalová. Please applause for her. And Marcela Kamenská. Yeah. And many other people from Project Management Office of CIIRC. I would like to thank to Mr. Jiří Ryšavý, who is making nice pictures to remember this workshop for next generations, and Marie Smatoňová, who did the website and the jingle and all these things. And I would like also to thank to our partners and sponsors who supported this event. I think for the next workshop we need to continue in attracting, let's say, French companies to support it and also to get some information, some results from this workshop for them. So thanks also to our partner like Valeo. I think we are at the end now. I have no more words prepared. I have to run because there is another video conference in 2 minutes. But thank you very much for attending. Thank you very much for staying with us till the end. And thanks to all of you, all the team and all the participants for active, efficient and useful participation. Thank you very much. Now the coffee is waiting for you. Thank you very much.
And also